T-minus 1 minute. T-minus 30 seconds. We are go for launch. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Good morning and welcome to NASA's Lunabotics 2025 Finals event. We are broadcasting live from this amazing Center for Space Exploration facility here inside NASA's Kennedy Space Center Visitor Complex here on Florida's East Coast. My name is Kurt Loit. I'm a NASA software developer and a robotics researcher, and I'm happy to be your MC, your narrator, and your color commentator for this event. I want to give a big shout out to all the teams and staff and guests that are here in person right here at NASA. The teams are just starting to roll in, but there are definitely a couple teams here. Teams that are here, let me hear you yell. Welcome to day 2. All right. We're also super excited for all of you who are watching our live stream from all over the world. Yesterday we had over 3,000 views of our live stream. So thank you for everyone that is sharing the link to our live stream. And thank all of you out there who are interested in NASA and who are interested in this event particularly. Please don't be shy about sharing our live stream link with everybody you know. Now, for anyone out there who is not familiar with NASA's Lunabotics event, I'll quickly summarize. Lunabotics gives college and university student teams the task of designing and building working prototype lunar construction robots. During the robotic competition runs that you're going to witness today, these robots are going to traverse complex and rugged terrain, and they'll dig and they'll transport fine particulate material or simulated moon dust from one location to another location. It's an exciting competition, and I'll be here the whole time to help explain what's going on. We had 35 teams compete last week in the Lunabotics qualifying event at the University of Central Florida over in Orlando. And the top 10 teams from that event are here this week to compete for the final grand prize. Now, these 10 teams are about to compete for the grand prize of the NASA's Lunabotics 2025 Finals event. Now, if you missed the stream yesterday, or if you were not here in person, I'll review what we did yesterday. Yesterday, as I mentioned, we have 10 teams that are competing. These are the top 10 teams out of the 35 qualifying teams. Yesterday, we got through one run of 2 runs that we're going to give each of these teams. Yesterday, we got through one run of 6 teams. We got through Michigan Tech, University of Virginia, University of Alabama, Milwaukee School of Engineering, University of Utah, and the Colorado School of Mines. That's what you missed yesterday. If you want to go back and review any of those runs, you can find yesterday's live stream on the same YouTube channel that you're watching right now. Not the same video, but the same channel. Just go into the live tab and find yesterday's live stream. It's going to be there, the full recording. 10 hours plus of footage. It's amazing. Go watch it. Now today, what we have on deck are the 4 teams that we didn't get to yesterday. We're going to be running the first run of these 4 teams: Purdue University, University of Illinois Chicago, University of Akron, and College of DuPage. After that, we will start the list over, and we will give each of these 10 teams their second official competition run. And according to the schedule, if we stay on schedule today, we will get through 4 of those 10 teams' second competition run. We should end up getting through teams 1 through 4, which is Michigan Tech, University of Virginia, University of Alabama, and Milwaukee School of Engineering. That is our plan today if we stay on schedule. Also, I want to mention in the middle of the day, we're going to have a lunch break. And during that lunch break, we're going to have a quick award presentation right here in our award area. We're going to give away the Systems Engineering Award to one of these teams that are competing this week. I also want to mention, and this is mostly for the teams that are in the room, but if there's any general public that is out there and exploring the visitor center and end up coming into this building, we do have some seminars going on in this building. We have a team from NASA giving a presentation on the ISRU pilot excavator. We also have a presentation on Artemis, NASA's return to the moon. We have a presentation on NASA internships. We have a presentation on systems engineering, NASA's systems engineering process. And we also are going to have a presentation today from Caterpillar on Caterpillar autonomy, the journey of command for hauling. So that is what you missed yesterday and what is on the schedule for today. So as teams roll in and get reacclimated to their pits and their robots and start working on the robots, you'll see a lot more activity here in this room. And we will check with the pit boss to find out exactly when the first run is going to start today. The first run today being Purdue University. So stay tuned. We're just going to show you some live shots of the room and of the arena while we get ready for the first team to run. So thanks for watching, and don't go anywhere.
Did you know there's been over 1 million registrations in NASA's virtual guest program since May 2020? From your neighbor to the Crew 5 astronauts, you might be surprised who is a NASA virtual guest.
Do you have Mars 2020?
I do. Do you have James Webb?
Sure do. Do you have Crew 5?
Well, I've got it here, and you guys have it here, but I missed it here.
We conducted over 200 science experiments and technology demonstrations on our mission. We loved being part of Expedition 68. We even remembered a virtual guest passport for Einstein, our freefall indicator, but we forgot to register. I missed the stamp.
Even if you're doing existing research, never miss a stamp from NASA's virtual guest program. Whether you're en route to the International Space Station or located anywhere around the globe, register at nasa.gov/virtual guests to receive updates on missions and milestones. As a virtual guest, you will receive curated resources and a stamp for your passport following a successful launch.
Remember, you only get the updates and stamp if you register.
I joined. I won't miss it next time.
All right. I was able to grab one of the students out of their pits who was working on their robots to do a quick interview. Let's start out with what team are you from?
I'm from Milwaukee, the Milwaukee School of Engineering.
MSOE, awesome. And what's your name?
I'm Garrett Gritzmacher.
Nice to meet you. So MSOE is one of the teams that ran yesterday, and we were just unable to do an interview, so I'm going to try and catch up on my interviews this morning,
All right.
if possible. So to remind the viewers, your robot was the one that had the 4 bucket drums, and it had the arms that lowered down. I forgot to ask you, what is your role on the team?
So right now, I'm the newly elected electrical sub-team lead, and I also do outreach coordination. So
Awesome. I love outreach.
who doesn't? It's fun getting people excited and drummed up about stuff.
I also love electrical because my degree is electrical engineering.
Well, there you go.
So converted to software though, but I'm no judgment on electrical. I love it. So what do you want to tell us about your run yesterday? What worked, what didn't work, and what is the team working on right now in order to get ready for their second run?
Yeah, so I was the one piloting it in the control room. We really tried our best to make do with the problems that we faced. We, on the regolith in the preliminary runs, was much more. It didn't seem to have as much issues. It didn't compact as much.
And that's at UCF in Orlando, the preliminary runs.
Yes.
So it's a different bin.
100%.
Different simulated, at least slightly different.
Yeah, well, we found very different.
Okay.
We could turn on the other stuff. We hit this issue a little bit with our stepper motors not quite keeping up, but it wasn't too much of an issue. We could fix it. This time, though, our stepper motors just could not fight.
Okay, so to remind anyone who was watching yesterday, your robot has the 4 corner wheels. It has 6 wheels, but the 4 corner wheels actually steer,
Yes.
and so they can tilt in and then spin in place. So what we were seeing yesterday was they were out of sync or completely almost completely turned around. So that what you're saying, I think, is that it wasn't an electrical problem, it wasn't a mechanical or software problem. It was actually resistance of the regolith actually turning those motors to a spot that they shouldn't have been in?
A little bit of both. So
Okay.
that's what exacerbated the problem. We found the root cause actually lies in our logic and how we go through the stepping motors. So instead of actually holding a step until we properly reach it, so the encoder reads back the position that we are actually in, and our code simply goes through in a loop and just keeps going through each step in the motor. The problem is with that, if we skip any steps, so if the shaft doesn't actually spin and we come back around, that's the same thing as stepping in the opposite direction. So we're fighting ourselves. So if force is strong enough to hold it in place, we actually assist it, which is why we think it does that giant backswing.
Gotcha.
So we get a big momentary force. It actually adds to it as each time we go through that loop, it's stepping in the wrong direction. It's not enough to keep pushing as it goes through, and it hits here and it goes back. And we're actually adding to that force is what we think is the issue.
Okay.
So
Okay.
it back swings until it can catch back up with itself.
All right. We went pretty deep there, and I didn't intend to go that deep, but that's okay because half of our audience is highly technical. You know, we've got
There you
NASA engineers watching, we've got other teams watching. The point is, you know, you understand what happened, and that's a very important thing to point out. Is you had the data in front of you. Did you understand live during your run exactly what was happening, or did you analyze the data later and figure out what was happening?
We had to analyze it later.
Okay.
Quite a bit. The footage from the cameras, the angles, we saw angles that we didn't get to see. And we actually had some really close angles on what our wheels were doing. And 100% we realized it couldn't have just been pushing force. We thought before it was just enough force to push it. But here there was moments where it was contacting. Then it had a bit of time where it really shouldn't have been pushing that hard against it, but it went almost 180.
It still
So
spun
we're
around.
like,
Yeah,
okay, there has to be some sort of logic
yeah.
issue here.
I was like, something's out of sync.
Yeah.
Okay. So this is the engineering process. I mean, not only have you spent the whole entire academic year doing following an engineering process of designing and doing engineering trade-offs, and then building, and then testing, and then fixing things that broke, and maybe redesigning, maybe going all the way back and redesigning things that broke.
Yep.
Now you're actually in the competition, and you're still following a logical engineering process to troubleshoot, look at data, understand the problem, and then the final step now is in the pits. Your team is fixing what you found, what you know the problem is, and let's hope that you have a really great second run. So your second run
Thank you.
is going to be what, tomorrow morning?
No, the last run today, I believe.
It's the last run today.
5:30.
All right. I'm excited for you guys. I will let you get back to the pit and finish working on your robot.
All
Thanks
right.
a lot for your time. Great to meet you.
Of course. Thanks. Great meeting you too.
Good luck.
Thank you. All right.
As our teams today start getting ready, their robots ready for today's runs, I'm just going to go over some Lunabotics details for maybe some of those who are watching that aren't familiar. We are broadcasting the Lunabotics finals here this week, but Lunabotics is an annual event that actually spans the entire school year for these teams. It requires all of these college and university students to apply NASA's systems engineering process to design, develop, build, and test a prototype lunar robot. Before being allowed to compete here this week with their robots, these student teams had to prove to our judging staff that they were progressing throughout the entire school year. All of these student teams have previously submitted, throughout the school year, they've submitted STEM engagement reports to show off the outreach that they have done in their local community. They have submitted systems engineering papers to show off the NASA's systems engineering process that they have followed in the design and construction of their robots. They also have submitted proof of life videos towards the right before, I guess a few months before the event started, just to prove the progress that they had made on the actual construction and testing of their robot, to prove that they do have a working robot and are worthy of coming here in person to compete. The robots in this competition are all designed to dig lunar soil and then construct berm structures or hills. Berm structures are going to be useful on the moon in order to protect sensitive systems that we place on the moon, like lunar habitats or propellant tank farms, and to protect those systems from rocket blasts that occur during either lunar landings or the subsequent launches off the surface of the moon. The piles of lunar soil that we might want to create on the moon are also going to be useful as protective coverings to insulate sensitive systems from either the sun or from destructive energetic particles and harmful radiation. I mentioned earlier that Lunabotics competition requires these college and university students to apply NASA's systems engineering process in order to design, develop, build, and test their prototype lunar robot. But what does that actually mean? I'm assuming that people outside of the engineering industry probably don't know what we're talking about. Well, systems engineering focuses on designing and building and managing complex systems. And since rockets and spacecraft and satellites and interplanetary robots are all pretty complex systems, NASA has over the years become quite proficient at using the systems engineering process. And so that's the process that we're actually teaching these students and requiring them to follow throughout the school year as members of this competition. I mentioned that these robots are all designed to dig lunar soil and then use that soil to construct berm structures or hills. Well, there's a special scientific term that we often use for lunar soil. It's more commonly called regolith in the space industry. And regolith is a soil on another planetary body that's any place other than Earth. So the moon has regolith and Mars has regolith, but you can really just think of it as moon dirt or Mars dirt. Back during the Apollo program in the 70s, the Apollo astronauts only brought back a few buckets full of lunar regolith, and we haven't brought back any Mars regolith at all, at least not yet anyways. So we are testing these robots on a bed of simulated lunar regolith rather than on the real thing. But forgive me if I slip and just call it regolith this week. Our simulated lunar regolith is actually volcanic rock that has been crushed to a fine powder. It turns out that this material actually makes a pretty decent stand-in for lunar soil. It's light and fluffy on top, sort of like talcum powder. And it's pretty hard packed underneath the top few inches, which is exactly how lunar soil feels. Throughout this event, anyone who goes into the hermetically sealed Artemis Arena, which you're seeing on the screen right now, They must wear protective garments along with eye protection and masks due to the small particle sizes that can become airborne, and also due to the possibility of skin and eye irritation. The fact that Luna Regolith, along with our simulant, is light and fluffy on top and hard-packed underneath, makes it fairly interesting to interact with. Your robot is going to sink down a few centimeters or even a few inches to get down to that hard-packed surface, and then you can drive around on that hard-packed surface, unless your driving actually loosens up that hard-packed material and makes it light and fluffy too. So in that case, your robot may actually sink down and get trapped in the deep, fluffy material that you've created. But that's not all. This stuff is more complex than it already sounds. The hard pack material is actually harder than you would think. And this is because the individual particles are created by energetic impacts on the moon. And the simulant that we've created is also similar in nature. The moon does not have atmosphere. It doesn't have running water. It doesn't have these processes that wear the resulting particles like we have on Earth. So each particle on the moon is jagged in shape, and so are the particles in our simulant. These jagged particles, when they settle in together and when they pack together under the weight of the material above it, they interlock like puzzle pieces and they become pretty difficult to penetrate. They actually resist your digging forces. This makes digging of the material beyond a few inches deep pretty difficult. Now, as you watch this competition through the week, you'll notice that student team solutions vary. All these robots are not the same. Student teams are trying to think outside the box and come up with new ways to solve the problem of digging lunar soil and then constructing these berm structures or hills out of the excavated material. Every year throughout this competition for these students, these teams perform full-blown systems designs complete with engineering trade-offs. They don't just throw a bunch of stuff together and hope for the best. And the rules of this competition really encourage the teams to perform these engineering design trade-offs. And Lunabotics really does teach these students about real-life engineering processes, as I've mentioned. You see, engineering is actually a mix of following a strict logical process combined with creativity and out-of-the-box thinking and trying crazy ideas. And that's exactly what these students are doing throughout the year and even this week here during the event. Here's an example of an engineering trade-off that all teams have to perform for this competition. All 35 teams that performed in the qualifying rounds last week and then the 10 finalists this week, they have all performed this trade-off. The Lunabotics rules state that each team's solution must fit inside a 1.5 meter by 3/4 meter by 3/4 meter box. That's about 5 feet by 2.5 feet by 2.5 feet. So the physical size of these robots has a hard limit. And so various ideas and solution that a team comes up with has to somehow fit within that physical size, or they just have to abandon that idea. They just can't, they have to meet that rule. Another example of a hard limit is the weight of the solution robot. The rules state that the solution has to be 80 kilograms or less. That's about 175 pounds. So again, all the ideas and solutions that a team might come up with early in their school year has to somehow end up weighing 80 kilograms or less. So if you take just these two rules, the size limit and the weight limit, they work together to limit the onboard power of these solutions, because if you think about it, batteries tend to be really heavy in general. And so teams have to trade off how much of that 80 kilogram total mass they're going to allow for the batteries and make sure they reserve enough mass for the rest of their robot. Another big design trade-off for teams is that they have the option of making their solution way lighter than the 80 kilogram maximum weight if they want. And a team might do this because the largest portion of their score, a full 50% of their score, is actually based on how big of a berm they create divided by the mass of the robot, plus how big of a berm they create divided by the power used by the robot. So in other words, a majority of their score isn't just based on the size of the berm that they create, it's actually based on the size of the berm they create as compared to the robot size and power. And so that means a smaller, lighter robot that uses less power but is still capable of creating a reasonably sized berm could potentially score very well in this competition. That's why you might notice that some of the Lunabotics finalist robots are bigger and some are smaller. These are some of the trades that these students are performing. Another design decision that used to be a big trade-off for teams, but now pretty much all teams just do it, is autonomy. Autonomy means letting the robot think for itself and control itself. Autonomy requires additional sensors and additional communications and additional power. And autonomy is just not trivial to make work. But the reason most teams actually do autonomy in this challenge is because we purposely have made autonomy a full 30% of their final score. We are actively and strongly encouraging teams to create autonomous robots rather than manually stick driving them during this competition. Now, let's talk about how runs work and scoring in this competition. We are performing actual scored competition attempts or runs inside our simulated regolith bin this week. Each team is going to get 2 separate scored runs inside the simulated regolith bin. And no teams are allowed any practice time inside the bin. So the first time they put the robot in this bin, that is a scored run, no practicing. So teams have to be ready, they have to be fully tested and confident in their work when it's their turn to run in the bin. Now once each team performs 2 30-minute long competition runs, the scores from both of those runs are going to be added together to form their event score. We don't use the best run score, and we don't use the average of the 2 run scores. Their final score is purely a summation of the scores from their 2 runs. So it's very important for all teams to have 2 good runs in order to be competitive here in Lunabotics finals. Now, the regolith bin is divided into different zones. There's the starting zone, which is in the upper left side of the screen right now. The starting zone is where each robot starts their run as if it was just placed onto the surface of the moon by a nearby lander. Beyond the starting zone is the obstacle zone. The obstacle zone contains craters and boulders. That's in the upper right. It's to the right of the starting zone, which is in the upper left. So the obstacle zone, which doesn't actually have orange lines around it, the area outside the upper left corner is the obstacle zone. The obstacle zone has craters and boulders in locations that are previously unknown to the teams. And all the robots have to pass through the obstacle zone before they are allowed to dig. Now, on the right side of the screen, the upper right quadrant is our excavation zone. This is where the robots are allowed to dig or excavate this simulated lunar regolith. Beyond the excavation zone, which is in the lower left part of the screen, that is our scoring zone or our construction zone. This is where the robots need to offload or dump the simulated lunar regolith that they excavated in the excavation zone. And robots are allowed and encouraged to go back and forth between the excavation and construction zones as many times as they want throughout their 30-minute long competition run. Now, there's a subtlety on the screen here. The scoring zone for constructed material is inside the 4 orange poles. But you'll notice the orange line is a couple feet outside of the orange poles. That orange line is basically a line that the robot has to excavate to the right of that line. So since the excavation zone is in the upper right of the screen, there's several feet worth of buffer between excavation and scoring, which requires the robots to move the regolith all the way into the scoring zone and not just sit in one place and perform the entire operation. It makes it a little bit more realistic. Although even though our Artemis Arena is limited in size, we're able to kind of force these robots to drive back and forth instead of just sitting in the middle. So that's kind of the overview of the run, the operation that these robots are performing. And if that doesn't sound difficult enough for these robots, we've actually made things even harder for these competing teams. We sequester all the team members who are monitoring and controlling the robot inside a completely isolated room, the Lunabotics Mission Control Room, which is far away from the competing robots. We do allow teams to choose from 2 optional lunar camera live feeds that they can turn on if they don't mind the point penalties that we apply for using these cameras. There's a live view from our control room. The isolation and the camera penalty forces a lot of teams to add onboard cameras or other sensors directly to their robots. But that's not exactly free either, because we monitor all of the network traffic between the Lunabotics Mission Control Room and the robot during their run. And we do apply point penalties for higher bandwidth usage on that network. But the more intelligence that teams put on board the robots, the less commands and data need to be sent back and forth between the robot and the human users. So adding more intelligence to the robot actually helps teams maximize their scores in this area. So to summarize, the object of this competition is to create as large of a pile of simulated lunar regolith as they can within 30 minutes. And then our engineers will perform a 3D laser scan of the construction zone, both before and after each 30-minute run. And they will use some cool 3D scan visualization software to precisely calculate the volume of the berm that each team has created during their run. And that berm volume is an important part of the team's final score, but it is not the only part. There are a lot of variables that go into the final score, as I have mentioned. So that is an overview. I was going to say a quick overview, but it was not quick. That is a fairly detailed overview of NASA's Lunabotics competition. So a little bit of a tease of what you're going to see throughout the rest of the day. So I did mention earlier that the Purdue team is going to be running first, and they have left the pit. They have left their pit. They have made it through their safety inspection and communications inspection, and the pit boss has sent them out to the arena. So we should see that Purdue team enter the arena with their robot and enter the mission control room with their students that are going to be controlling this robot. So don't go anywhere, because in just a few minutes we should be able to start the Purdue, the first of 2 official competition runs for Purdue University.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
Go. Prop, go. TDA, go. Fido, go. All right, folks, go for launch.
Our destiny is always to go and see what's further and what's next.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills.
It's been 50 years since we've been to the moon, and we've got a great program called Artemis. We're going back. The Apollo program was a test for the American people that you can do what you set out to do. All it took was turning to it and making it happen.
We are go for a mission to the moon at this time.
Engines on 5, 4, 3, 2, all engines running. Launch commit, liftoff. We have liftoff 49 minutes past the hour.
I think the characteristic that I remember most of the Saturn V was the noise. The noise was enormous and it was almost impossible to communicate.
We're go, train tight, we're go. Tranquility Base here. The Eagle has landed.
The landing to me was a great celebration. The nation was almost euphoric.
That's one small step for man, one giant leap for mankind.
There are so many things that we could eventually learn about our universe and the spacecraft that we use exploring.
We are a nation of explorers. During Apollo, we were on national TV literally every day because we were doing something visible that Americans could see and they could feel and say, look what we are doing. And I believe Artemis is going to come up and say, look what we are capable of and what we are doing now.
Artemis will stand on the shoulders of Apollo. They're going to have the eyes of the world on them when they start down this trail.
The science of a space flight is one that will continue to inspire. Going to the moon generates technology, more communications, more computer technology, more sophistication in manufacturing that help us in everyday life.
We have a generation that is ready, a generation with that technology, a generation with the education. Artemis represents the future in space. It is our next big step, and it is time to take it.
The crawler transporter is it's a machine that goes and picks up the mobile launcher, the SLS rocket with Orion. It's basically the cornerstone of the mobile launch concept. Without the crawler, you couldn't transport the mobile launcher and the vehicle from the VAB to the pad or the pad back to the VAB. And it was designed and built for the Apollo program to move Saturn V's to the launch pad. Since then, we've modified it and used it to move the entire shuttle program. And after the shuttle program, we did extensive modifications, and now it's to be used to move Artemis to the launch pad. The crawler is 136 feet long from end to end. It's 114 feet wide from the edge of the truck to the other edge of the truck. It weighs 6.6 million pounds. It has the power to do 2 miles an hour, but you never want to go that fast. Generally, we're around 0.83 for SLS. Artemis will be one of the heaviest loads we've ever carried and one of the tallest loads we've carried. I am exceptionally proud of our team. They're very talented, they're very committed, and they're just all around good team. I think any problem that crops up or anything that comes up, we'll fix it and we'll get moving again. And again, it starts right here with the crawler. So if we do our job and everybody else does theirs, man, we're gonna have a successful launch. We're going back to the moon. This is gonna be just fantastic.
You are watching NASA's Lunabotics 2025 Finals, day 2 of 3. On the screen, you're getting a close-up view of the Purdue robots, some of their autonomy sensors, some depth cameras, possibly. We are several minutes into Purdue's 10-minute setup time period. And during that 10-minute setup time, we have students in the arena working hard, and we have students in our mission control room also working hard. They're setting up their computers, their laptops, their tablets, joysticks, networks. They're powering on their robot, testing, verifying communications. They will verify commands are working, data streams, telemetry is all working. And they have 10 minutes to basically power up their robot and set up their command and control workspace and verify it's working, and also troubleshoot and fix any issues that might crop up. This is going to be Purdue's first run of 2. We see students in the arena with their tape measures, setting up visual targets, black and white barcodes essentially, for the robot to look at with its cameras and then calculate where it is in the arena based on that camera feed. Pretty commonly used technology in the autonomy world. So what you're seeing is the students in the arena getting out of the way and probably calling on the radio to the students that are in mission control to look at the computers and verify that the robot is seeing the barcode and able to calculate its position. Now this robot is most definitely set up for autonomy. As I said, this visual marker is just one part of the autonomous system that is on board this robot. There's a visual marker, and in this view it's hard to see, but there's a visual marker on the far left side of the screen in that view, that side view. That marker in this view, the lower left side of the screen is the deposit area, the construction area. I also like to call it the scoring area. Any material that is deposited inside those 4 vertical posts, those orange and white vertical posts, that material that's deposited in there will be scored. It will count for this run. And the students have placed another visual marker in this area. It's on the far left of the screen. And so the robot will use this second visual marker, presumably, to line itself up and know exactly where it is on that side of the arena. And these markers are large enough that the robot will be able to see them even when it's further away back in the excavation zone. So I presume the students are using these markers both during the excavation portion of their run and the deposition or scoring portion of their run. 2.5 minutes remaining to get the robot running and verified everything's working. Now if we look back at the students in the control room, during their setup time, they do have access to a couple of live camera feeds that we are supplying them. on the large monitors in front of them. Control room. So the two large monitors on the left side are provided by Lunabotics to any team that wants to watch those camera views, those camera feeds from the arena. But those are optional. Teams are allowed to use them or not, and there is a point penalty if they decide to use them. That's during the run. Right now we're in the setup time, so those cameras are basically free for use during the setup time. But as soon as the run starts, we will notice a lot of teams will turn those monitors off right on cue. So obviously this Purdue team is not going to be using the two camera feeds that we are providing them, the two optional feeds. They're not going to take that point penalty. They're going to run completely from data, camera data and other data that's streaming from their robot. And in the last few seconds of setup, as those seconds wind down, we will look at the robot in the starting position. It has a color code system. It has an avionics box on the back of the robot, basically a box full of computers and other electronic equipment. You can see it's lit up blue right now. The team tells me that blue means the robot is in manual mode. But if that color changes to green, for example, the robot is in traversal automation or scanning barcodes. So the 30-minute run has started for Purdue. The robot is telling us it is in autonomous mode, but officially our Lunabotics judges are not looking at the light on the back of the robot. Officially our judges are watching the students in the control room. And if we cut real quickly back to the students in the control room, we can see, just like the judges can see, that the students are not touching their computers, they're not touching their joysticks. Control room for just a split second, please. The students in the control room are watching the robot perform. And you can see their hands off. This is what our judges are officially looking at in order to notate on their score sheets whether the robot is autonomous or not. But we, the viewer, get the advantage of also seeing the light on this particular robot, which is green, saying that it is in traversal mode. So it just scanned the starting zone. So I suspect it was looking for rocks, and I suspect it's now going to drive across the obstacle zone. This is the portion of an autonomous run that can be hard to watch, because it would be so easy to just take over control with the joystick and just start driving this robot. But if the students do that, if they give up on automation, they're giving up hundreds and hundreds of points. So they students are always very cautious and very conservative. All right, looks like the robot's back in manual control. It turned blue, and it looks like they're driving the robot manually right now. So they're driving the robot manually through the obstacle field, because if they wait too long on the autonomy to work, it's going to waste too much time. Looks like they are getting through the obstacle field. And now the robot has transitioned into the excavation zone. This excavation zone does have a few obstacles in it, and the students are backing the robot up so that the digger is in the upper left and the depositor, the dumper, is in the lower right. That keeps them from having to turn the robot around throughout their run. All right, now let's see if the students are going to put this robot back into autonomy in order to complete the rest of this 30-minute run. They're only 4 minutes into this run. Okay, you can see their rotating bucket ladder digging system has started spinning up, and it is lowering into the ground. It looks like they're still blue though, so well, I am seeing the blue light, but I'm also seeing the students not touching their joystick. So this, based on the students' body language, this does appear to be autonomous right now. You can see this robot has a conveyor belt in the middle. We've seen that several times before. Seems to work pretty good. Multiple teams have come up with the same design with a bucket ladder system that's just a kind of a conveyor belt full of digging buckets with teeth. That's purple, so that's automated deposition, they tell me. And again, I do not see any hands on computers or joysticks, so I do believe that light every time a robot that's in autonomous mode pauses like that, there's a high chance that it's doing some pretty detailed calculations, possibly deciding exactly where it is in 3D space compared to where it wants to be, possibly calculating the safest path from point A to point B. There's lots of calculations an autonomous robot might perform. All right, the robot is excavating another. You can see the hole that was left by the prior excavation run right there in front of the robot. So they're going to make another hole right here. It looks like a little slot trench. And this does appear to be autonomous. So it's looking like this team is going to get points for multiple cycles of autonomous digging and autonomous deposition is what it's looking like. One of the things we tend to look at in order to compare one team's run to another team's run is we like to compare the size of the pile, the size of the berm that was left by the robot, but there are so many other variables involved. If two teams end up creating the same size berm, but one of them uses autonomy, even partial autonomy during that run, and another team doesn't, well, the autonomy points are worth a lot, so that definitely gives the first team a huge scoring advantage. All right. This Purdue team is running fully autonomously, and they're on their way to, I think, getting a lot of autonomous material deposited into the scoring zone. We're only 9 minutes into the run, and you can see the pile they've created there already on the left side of the screen. So in the next 21 minutes, this Purdue team has the opportunity to create a pretty good sized pile there and be a real competitor. So the Purdue nickname or mascot is the Boilermaker. And if you aren't familiar, a Boilermaker is kind of an old school kind of thing. It's a tradesperson who fabricates steel, iron, copper into boilers or other large containers. And these boilers hold hot gas or hot liquid. So now you know what a Boilermaker is. So this bucket ladder digging system is mounted on a linear actuator that drives the system down under the surface, so it can choose the depth. It can start out digging shallow for the first pass, and it can go deeper, or it can stay at that depth and just add length to the trench with subsequent passes, which I think might be what this robot is doing right now. I think each pass is moving forward a little bit more. So the robot is completely keeping track of where it had dug previously. And now that the robot has backed up, we can see the trench that has been left behind. It just keeps getting longer and longer. It's not getting super deep yet, but we got 18 and a half minutes left. It'll be interesting to see if this robot, when it basically reaches the end of this cut, is it going to start over and go back over that same cut deeper? Oh, it's just okay. So it's gonna choose a fan pattern. So now it's going to be starting here probably and digging another finger kind of out in a slightly different direction in order to spread out its digging in the digging area. It can be important to spread out your digging, because we did notice this a few times yesterday. If you focus your digging in one particular small area and then you're efficient at it, you're basically digging a hole in this one spot, which could cause you trouble later. So it looks like this Purdue team has designed their digging pattern to be kind of fan-like, where they kind of start from a central location and then dig trenches out in several different directions is what it's looking. I think the robot may have lost track of the deposition zone there. Now, as a skid steer robot, this is interesting to watch a skid steer robot turn in place, The wheels on one side spin in one direction in sync with each other, and then the wheels on the other side spin in the opposite direction in sync with each other. Now this team is seeing that this robot is doing something that they probably do not want it to do, but they have to make the hard decision. Just let it go, because once it comes around, it'll see the marker that they had placed. Oh, it seems the right wheels on this robot seem to have stopped turning. I don't know if that was on purpose. Okay, they're turning again, so maybe that is part of their. Okay, they just took over manual control. So they decided this is too much. We don't need those points that badly. Let's just take over manual control. Okay, so they lined it up manually so that it could see its marker, and then they put it back into autonomous mode. So this is on autonomous dump, but they did have to step in, and so the judges are taking note of that. Anytime a team steps in and takes over manual control, the judges in the mission control room are watching those activities and making note so that they're scored appropriately, so that we give them just the autonomy points that they have earned. So now it looks like we're continuing the fan pattern by digging in a new direction now. We're halfway through this run for Purdue University. This side view shows not only does it show the pile that this robot has placed into the scoring zone, but right now around the robot you can see a little bit of dust. At first glance you might think that is smoke coming from the robot. It is very likely dust, because this digging operation, all of these robots, when they dig or drive, there's a potential to create dust, and that is one of the reasons why all of the personnel that are inside the Artemis arena have to wear the protective gear. And it should be noted that teams are scored on the topic of dust. Teams are scored in two different ways. When the teams take the robot through the safety inspection before they're allowed into the arena, one of the things that the safety inspection judges are looking at is the design and the implementation that teams have implemented into their robot, covers and such, to attempt to minimize dust lofting in our arena. That's part of the dust score. But then during the actual 30-minute run, our judges that are actually inside the arena are actually watching dust lofting in real time and making note of that and giving teams an additional score based on how much dust did they actually lift up into the air. And that's essentially a penalty. We are encouraging teams to not be lofting dust into the air. The more a robot can dig on the moon without creating a huge dust cloud, that is highly desirable for a lunar excavation robot and a lunar construction robot. And so we are encouraging teams, based on this scoring, to do the best they can to try not to loft dust into the air. The teams have taken over manual control again. They're down to 12 minutes, and so apparently they've decided that maybe gotten a little impatient with the autonomy software, or maybe had some issues that they decided were not worth living with, and so or they've decided we've got enough autonomy points, let's try and maximize our berm size now. So they're manually driving the robot now with the joystick. That previous dump was further back to the left on the screen right now. It's possible that concerned the students. You don't want to dump. If you end up dumping outside of that scoring zone, it's kind of a waste. It's a waste of time. It's a waste of energy. You're not going to end up getting points for any material that is outside of those 4 vertical orange and white posts. Okay, the students are now digging manually. Hands on joysticks, manually driving this robot. The fact that some teams are doing full autonomy and having success, some teams are not even trying autonomy in order to try and maximize their burn pile, and that some teams are doing a mix. Part of their 30-minute run uses autonomy and part of it doesn't. These variables will drastically change their final score. And so my point is, we will be looking at the sizes of the berms that these teams create, but the team that makes the biggest berm size is not necessarily the team that's going to win this competition because all of these other variables. If a team manually creates the largest berm and then another team autonomously creates a smaller one, it is possible, based on the point system and the rules, it is possible for the smaller berm to actually win this competition just because autonomy and other variables are so important. Getting a little bit of wheel slip there. I wonder if they were dragging their digging implement. Looks like they're trying to load up. They do have 9 minutes left. All right, their digger is fully out of the ground now, so they shouldn't have any trouble driving now. This robot, this angle shows the treads, a good angle of the treads on the wheels. This robot does have really good grip on the soil. When a skid steer robot spins in place, though, it does tend to push the soil sideways, so students have to trade off between having the most grip possible but also being able to slip when you want to slip. If you're turning, you do want the wheels to slip sideways, but not like in the normal direction. So wheel design and tread design is not a trivial task for any of these teams, and it's not a trivial task for the NASA engineers who are designing robots for the Moon and Mars. But one bonus detail that that NASA gets out of this competition is being able to see all of these different designs and to be able to kind of see what works and what doesn't, and maybe study them, and maybe learn some do's and don'ts before we send our own robots to the moon. This low angle also shows you their digging area, how ruddy it is. There are high spots and low spots. There are trenches. There are wheel tracks that are starting to get kind of deep. But thankfully, this robot isn't getting stuck in that. Oh, that was a big load. That was a lot of material in that one load. 7 minutes left for Purdue's first run. I love that the judge is laying their clipboard on the screen here, and you can see all of the notes that they're taking during this run. I'm told that all the notes that judges are taking on these robots are going to be shared with the teams at some point, which is great. Okay, 6 minutes left. I'm not sure where they're going. The students are manually driving this robot right now. Whoa. Is there a rock right there? That took me by surprise. There's a small rock there that really gave that robot some grief.
Good morning, everyone. We have our first seminar. Rob Mueller, our head judge extraordinaire, is going to be giving a seminar on ISRU, which is In Situ Resource Utilization, which is why we do Lunabotics. So that's starting right now in the seminar room, 7030.
If we look at the control room for a second, we can see the students working on something, typing on their computer. I think they might have gone back to the starting point so that the robot could get a lock on its position. You know what? They're going back for some more autonomy points. Remember at the beginning of the run when they actually manually drove the robot through the obstacle course? I think they're going back in the last 5 minutes of their time to get the autonomy points for going through the obstacle field. This is kind of exciting. So they're hands off. Nope. They took over manual control again. They tried. I'm really impressed that they tried that again, because that was a bit risky. It took how many minutes of their time? Definitely took a couple minutes to try that. If they had succeeded, they would have gotten, I don't have the point system memorized, but they would have probably gotten hundreds of points added to their score. So kudos for trying that autonomous traversal of the obstacle field twice in one run. They do have 3 minutes left to do some more digging. Now they're actually digging toward the camera now, so we'll be able to get a front view of the digging system this time for a change. So it goes down, the digger goes down to a certain depth, and then the robot drives forward, and it stays at that depth. It's going deeper than they are still manually driving this robot. There you can see things shaking. When they get to a certain depth, as I mentioned earlier, this light fluffy stuff becomes pretty hard, and it really resists your digging, and that's when you're going to see robots shake when they get to that depth. Now when these wheels go down, it's going to force their digger down unless they compensate. They went down into the hard stuff and bound up their digger. looks like. Let's start it back up again. All right, we're getting low on time. They have a minute and a half. The students need to decide how much time they need to lift up their digger and drive. Not only lift up their digger, but to drive backwards, because they're facing in the wrong direction to dump right now. Lift up their digger, drive backwards to the scoring zone. Okay, they're starting to turn their robot closer to the proper direction. Now they're lifting up their digger. 1 minute remaining in the last minute of Purdue's first run. Nope, they're still digging. How many seconds does this team need in order to drive back to the scoring zone and deposit their material? Right now they have about 50 seconds remaining. Okay, it looks like they stopped digging and are lifting up their digger. Things seem to have paused though. I want to point out the wheel that is closest to the camera, the rear right wheel. Notice you can see the treads plain as day in the front right wheel, but the rear right wheel is basically packed full of regolith right now, regolith simulant, from this wheel spinning to a point where it's just picked up regolith, almost like a digging system. Okay, sad to see that this team was unable to come back and score this final load. But let's give Purdue University a big round of applause for an amazing run. And let's pop the camera one and show the pile that this team has deposited. That is a respectable pile. And this is just the first run for this team. So they'll get a chance to correct, tweak, whatever they want to do on their robot, software-wise, hardware-wise, sensor-wise, and perform a second scoring run later on this week. So looking ahead, our next team that's going to compete this morning is the University of Illinois Chicago. So don't go anywhere as the Chicago team gets their robot ready to go into the arena and compete. You're watching NASA's Lunabotics 2025 finals event here in Central Florida.
The imagery that we're collecting on Artemis 1 and the mission itself is preparing to carry humans to the moon. The Orion Imager team is going to be monitoring every aspect of visual spacecraft performance for the entire duration of the mission. The first time that we're going to be live streaming digital video from a human piloted spacecraft back down to the Earth from the vicinity of the moon. That's never been done before. What we'll be transmitting live streaming will be lower resolution, more compressed, because we have to fit it into a thinner pipe, if you will. Every one of these cameras is in its position where it is and is configured the way it is for a very specific reason. We're going to be monitoring anything that we can see with the cameras for spacecraft performance. The imagery teams at NASA are composed of dozens and dozens of very highly trained, very specialized people, engineers, technicians, analysts. If we can see it, we're going to try and keep an eye on it. Imagery has been invaluable throughout the history of NASA. We flew cameras on Mercury, Gemini, Apollo, all of that stuff that we saw with the astronauts around the moon. It helps us detect the unknown unknowns. It allows us to see things that we didn't anticipate happening before. So when we do fly people on Artemis 2, we can have a high confidence that everything is working the way it should.
Our moon. It seems so close in the night sky.
but getting there is really hard. But what if there was a way to change that? Only a few nations have successfully landed on the moon. As NASA sends astronauts back to the lunar surface, this time to stay, we will need to send science and technology instruments ahead of time to lay the foundation for human exploration. To make this happen, NASA is helping establish a commercial lunar economy. For the first time ever, there will be commercial delivery services to the moon. We are enabling American companies to send our payloads to the lunar surface for us. These delivery services will expand our capabilities for exploration, radically increasing the amount of science we can achieve. This high-risk, high-reward initiative will invest in and leverage the entrepreneurial spirit of American innovation to launch a commercial lunar marketplace, advancing technology and exploration for all of us. With this never-before-seen streamlined access to the moon, we will be able to make novel measurements and develop technologies that scientists have long wanted to do on the lunar surface. And as this new industry matures, this commercial delivery service for NASA and other customers could expand beyond the moon to other destinations in our solar system. And we can learn to live on another world because we are explorers.
Hi, I'm Janet Petro, the director of NASA's Kennedy Space Center in Florida. Hop in and let me show you what we're doing at Earth's premier spaceport. Let's go fly.
Our spaceport is proud to support the agency's goals to return to the moon in preparation for Mars. Our cooperation with commercial companies and international partners is greater than ever before as NASA embarks on a new and exciting era of space exploration. At Launch Complex 39B, the uncrewed launch of Artemis 1 was an exciting first step on our way back to the moon. Now, we are hard at work preparing the hardware, systems, and processes for the crewed Artemis 2 mission. Targeted for 2025, Artemis 2 will prove the Orion spacecraft and the Space Launch System rocket when the 4-astronaut crew ventures around the moon on a 10-day flight and returns safely to Earth. Meanwhile, we are launching missions to the International Space Station, continuing the research that helps us solve problems on Earth while proving capabilities we need for long-duration human space exploration. Microgravity, low Earth orbit offers a unique environment to study disease formation, test diagnostic tools and treatments, and advanced technologies like computers and robotics. NASA and our commercial partners are expanding the ability to launch crews, science, and cargo to the orbiting laboratory, which will ensure sustainable operations on the station for years to come. Nearby, in the Space Systems Processing Facility, teams are developing other exciting technologies we will need to live and work on the moon. Plant researchers are experimenting with new ways to grow food in space, and engineers are working on projects like 3D printing capability to build structures on the moon, rovers and instruments to find resources to help sustain a long-term presence, and electrodynamic dust shield technology that can repel the abrasive moon dust to protect our astronauts, their vehicles, and sensitive equipment. NASA's commercial providers help us launch a range of science missions that study our Earth, explore other planetary bodies, and reveal more about the origins of life and our universe. NASA works with both emerging and established commercial providers for launch and landing opportunities. These efforts benefit the U.S. economy and help grow the commercial market. By helping commercialize low Earth and cislunar orbits, NASA can reduce the cost to explore space and maximize benefits here on Earth. Another Kennedy team in the Space Systems Processing Facility is developing NASA's deep space commercial supply chain to procure the services needed to transport cargo, equipment, and consumables needed for human exploration of the Moon and Mars. For Artemis 3 and beyond, NASA will rely on commercial partners to support a regular cadence of moon landings. Our commercial partners are doing exciting work to develop the next generation of spacecraft and landers. The spaceport offers a prime location for companies like these to consolidate their manufacturing, testing, integration, and launch services in one location, helping them save costs while leveraging the spaceport's unique expertise and capabilities. Kennedy has supported growth at the spaceport through key power, water, and transportation upgrades and investments in fiber telecommunications. Through our master planning process, we will continue to forecast and plan improvements to enable responsible development into the future.
And I couldn't be more proud of all the people at the Kennedy Space Center who make this all happen. You know, the processing, the integration, the launch operations, all carefully working together with our partners, with the Space Force, and with our NASA programs. The future's coming fast. Kennedy Space Center is leading the way. We're not just launching humanity's future, we're launching to the moon and beyond.
You are watching NASA's Lunabotics 2025 finals event being held here in Florida at NASA's Kennedy Space Center Visitor Complex. On the screen, you're seeing the University of Illinois Chicago team in mission control. These students have 10 minutes, 2.5 minutes left out of 10 minutes to set up their command and control workspace in our mission control center. It's important to note that the students who are controlling these robots do not have, they're not in the same room as the robot. They don't have visual eyesight to the robot. The robot is in a completely opposite end of the building. And so the students who are monitoring and controlling these robots during this competition are completely isolated and have to depend on data coming back from the robot or 2 optional video camera live feeds that we will optionally supply these teams if they choose to take the point penalty. So here's a look at the UIC robot. This is a unique design. This is the only robot out of the top 10 that has a center-mounted plunging scraper hopper. These are my words. I don't know what they officially call it. I should ask them. It's a large bucket that's mounted in the center of the robot that can be used as a scraper, as a light scraper to just scrape off, the top inch or so. But from what I've seen, this team gets pretty aggressive, and they plunge this guy at a pretty steep angle. It's almost like a front bucket loader bucket, but it's much, much thinner. And the fact that it's center mounted might actually give them an advantage as this center mounted bucket feels resistance while it's digging. It's possible, I don't know for sure, it's possible that actually gives the wheels more grip as this bucket digs in and feels resistance from the digging. So looks like the 10-minute timer for University of Illinois Chicago's setup time has now expired, and we should see the clock reset after the students leave the arena, and only our official judges are left inside the arena. Our official timekeeper will reset the clock to 30 minutes, and we will start this run for UIC. This will be University of Illinois Chicago's first run of 2 official competition runs. The robot is starting in the starting zone. It will be required to traverse beyond the obstacle zone, avoiding rocks and craters in the obstacle zone, and then dig or excavate in the excavation zone, and then deposit material in our construction zone for scoring. These students have the option, each team has the option of running their competition runs manually, basically driving the robot manually with a joystick or keyboard or mouse, or performing autonomous operations, which will give them extra bonus points. So we will see in real time, we will watch the students in real time during the run to see whether they're hands-on, manually driving this robot, or whether they're hands-off and the robot is autonomous. All right, the clock has started. I see students typing on keyboards. This is probably an indication that they are activating some sort of autonomous routine. This robot does have two obvious cameras on the front of it, which is facing to the right, and it looks like another camera on the rear of the robot. Possibly those are the sensors used for autonomy. All right, we saw some motion. All teams in this competition are going to try real hard to perform at least some portion of their run autonomously, because the points are well worth the effort. But if these students are unable to get their autonomy software working within a certain time period, I imagine they're going to give up and take over manual control for the rest of the run. We see a joystick in the hands of one of the students. So they may be giving up on autonomy, possibly. Robot still is in the starting position. So real-time troubleshooting, real-time debugging, real-time problem solving is a skill that these students, all the student teams who are competing in this event are learning this week and last week during the qualifying rounds over in Orlando. On the left of the screen, this Mission Control Center view, are two monitors. Go back to that Mission Control. I'm talking about what's on the screen. Mission Control view, please. Mission Control. No, it's the students in Mission Control, please. Thank you. The monitors on the left of the screen, you can see one of the students controlling a camera. The students have decided to take in one of the cameras that we're providing and take a point penalty along with it. So both of those monitors on the left of the screen are house provided. Those are provided by Lunabotics, and teams are allowed to use those with a point penalty or to turn those monitors off for their run and completely depend on data and camera feeds directly from the robot. I am seeing some frustration right now, some body language that shows the students are definitely having some problems and trying to troubleshoot and correct the problems. This may not be fun right now as these students are experiencing problems, but the entire troubleshooting process and problem solving, this is all good experience for up and coming engineers. So even though it might not be fun right at this moment, these students hopefully will look back on this time and learn from it, and hopefully look back positively on it. The robot is moving. All right, they're driving the robot manually through the obstacle zone, and now they've got some time to make up. We're almost 7 minutes into this run, and the robot has just crossed over into the excavation zone, and you can see they're lowering their excavation, center-mounted excavation bucket, and the side camera shows how the wheels are interacting. Those back wheels are really pushing hard. And the overhead view shows the material in that bucket. Now they're going to raise it up. The students are controlling this view, but you can see how much material. This is a powerful robot. It pushed really, really hard. It went really, really deep. And assuming they can get that material back over to the scoring zone, that's a good load right there. Looks like a big old loaf of bread from this angle. No, this team does have a vibrating motor. Look how much material. This is one load. Look how much material they're about to deposit. That is a thick, thick cross-section of simulated lunar regolith. Now they're going to turn on the vibratory motor in order to vibrate. Oh, their dumper seemed to not hold its position, but yeah, it needs to hold that position. Now the vibratory motor is turned on because this stuff doesn't flow very easily. Like I said earlier, you realize that they went pretty deep. They got down. They actually used their vibratory motor when they were digging in order to break apart these small particles that really want to hold on to each other. So the vibratory digging allowed them to go pretty deep, and that material was still kind of holding itself together, which required a vibratory motor to make it break loose from its hopper. So 21 minutes remaining, and they've only dumped once. They've only deposited once, but you saw the time between digging and depositing was very short. So there's still a lot of time left for this UIC team to deposit a lot of material. You can see them lowering their digging bucket, driving backwards. You can see their vibratory. You can see how the material is the material looks like a fluid when that vibratory motor is active. And that's kind of part of the magic of having a vibratory motor helping you with the digging and the dumping. That vibration kind of fluidizes the particles and helps them flow. They're taking smaller bites out now. They're being a little more conservative. With 20 minutes left, it'll be interesting to see if they. Oh, I know. I just realized why it's being more conservative. They're in automation. They're doing autonomy right now. So when they manually operated this robot, they were very, very aggressive. And you saw how full that very first load was. These cycles that we're seeing right now appear to be autonomous. The joystick is not in anybody's hands. No hands are on any keyboards. And so this is fully autonomous cycles of digging, transporting, and depositing. So these students are getting some great autonomy points right now. Even though each load is small compared to what they can do manually, even though each load is small, the autonomy points are worth so much. It is worth doing. So the students are keeping an eye on productivity and deciding, is it still okay? They just picked up the joystick, so they decided autonomy wasn't. They definitely got some autonomy points over the last few minutes for sure. But they just picked up the joystick, and I suspect we're going to see some some really aggressive manual digging here. Yeah, that last load, it was actually unable to unload. So now the student is getting a long runway. Now we're going to, I think, see some aggressive digging. Nope. I'm having trouble deciding whether I think we're autonomous. I think they position. No, this is manual. Honestly, we don't know. The judges in the Mission Control Center, no. Yeah, it looks like the student is driving this robot right now. They have gone a little sideways. You can kind of see there might be some binding happening here. Nope, they recovered. That was an aggressive dig right there. Oh. There was something binding, but it seemed to break loose. There might be some tolerance there in the middle where things get a little bit sideways and hang up, but they got past that. And look how much material they're bringing back. This side view shows kind of how much material is already there. Now they're dumping, it has to lift up, and there's a bar there that it kind of has to get past. Oh, it fell down again. That's not the first time we've seen that go up and then fall back down. I wonder if there's supposed to be a brake there that is not working. All right, you saw that material did not move until the vibratory motor was activated. It's crazy how sticky. Sticky's not the right word, but it kind of looks like it's sticky material. It's completely dry. There's definitely no moisture in this material to speak of. But you saw how the high angle that this hopper was sitting at for a number of seconds, and no material fell out at all. And that's, as I was saying earlier, this material is, the particles are jagged and they stick together, and they kind of lock on and hold on to each other. And that makes it not only difficult to dig in, it also makes it difficult to transport and deposit somewhere else. Well, the obvious question might be, why doesn't everybody use vibratory motors on their digging implements? Well, I mean, that motor is not trivial. It takes power. It adds mass. It adds complexity to your software. It adds more things that can break down. So this is one of the many trade-offs that all of these teams have to perform. That load was even bigger than the prior ones. Look, I don't think they can fit any more in their bucket, honestly. That is a lot of material right there. And we're only halfway through. 14 minutes left in this run for University of Illinois Chicago. That is a lot of material. That robot is so heavy right now, but the wheels are big, and they have really big grousers, really big grippers to grip onto the soil. Man, that is a lot of material. The UIC students have to be happy with the amount of material they're depositing for scoring, even if they're not getting the autonomy points that they were hoping for. All right, looks like the students are going to pick a different spot to dig in. One of the downsides of being able to pull up a pile, a chunk of simulant that's this big, is it leaves a pretty big hole behind. And so that hole that you leave behind may actually cause you issues later. So this is why you see a lot of teams not digging in the same spot over and over and making sure that they cover the whole field, all the possible digging area. This overhead view is what the students are looking at right now in the control room. I don't know if you saw that, but it really did like a fluid, look like a fluid there. There were actually bubbles coming up from that material, bubbles of air when that vibratory motor was running. If you missed it, pay attention to it in the next run. It's really interesting to see this bed of material when it's in a fluidized state. It really does look like a liquid, and it acts like a liquid when it's in that state, when it's being vibrated like that. It's acting like a very, very thick fluid, I should mention, almost like like a lava, more like a lava than a water. All right, going back for more. 11 minutes left for University of Illinois Chicago on their first run. They're picking a slightly different spot for their next dig location. Sorry. Now you might see that material kind of fluidize and bubble from this overhead view. It almost looks like it's boiling. Another really full bucket. Not both the front and the rear are really full right now. This side view kind of shows the piles that this team has deposited, and the camera doesn't even give it justice. These piles are massive. the tip of that pile is about the same as the diameter of that wheel. And that wheel, I think, is, I don't know, 16 inches tall, give or take. You can see what looks like smoke, but that is very likely not smoke. It is just dust being kind of lofted into the air by this vibratory system. We do try and encourage students to minimize dust lofting by giving them, I guess, essentially penalties for lofting dust. So it's going to be part of the final score, and that's part of the final score for all teams. So this team is taking a little bit of a hit on their score for lofting dust into the air. But the brunt of all of these teams' score is how much material they bring and deposit into the scoring zone, divided by the mass of the robot, and also how much material they bring into the scoring zone divided by the power used by the robot. That particular digging attempt fell short for some reason. I think their bucket went way, way deeper, higher angle than they intended, and it just kind of hung up the whole robot. Look at the front wheels of this robot lifting up in the air. Only the back wheels are doing any good right now, but they are doing a lot of good. Look how deeply the rear wheels of this robot are digging in. But as long as they keep that vibratory motor active when they pull the bucket up, it'll be able to pull up. Seven minutes. We're inside 7 minutes for University of Illinois Chicago's first run. It's been a minute since we've seen productive motion. There we go. Their robot was pretty deep there. You can see their frame of their chassis kind of dragging. You know, they've got that part, that center part of the excavation zone really, really fluffy. But thankfully they are not getting stuck in it. This is a skid steer robot. So the wheels, when the robot turns, the wheels basically have to slide sideways. But you can kind of see that the design of these wheels allows for sideways sliding while also having, you know, lots of grip in the forward and reverse direction. The large diameter of these wheels, I believe, also gives them a lot of surface area that's gripping the soil. But I'm not going to presume that there's a magic, perfect wheel size that is the right answer. There's so many other variables. For example, your software that is driving the wheel motors. You know, if it's driving them too fast, if it's accelerating too fast, regardless of your wheel size. You know, if you don't kind of take it gentle, if you accelerate too fast or try and drive too fast, faster than the inertia of your robot will allow, you're totally going to slip in this regular simulant. So there's so many variables that add up and compound and end up making a really good system that can operate in these conditions, or a system that has trouble operating in these conditions. We're down to about 4 minutes left in this run for University of Illinois Chicago. They're gaining another really full bucket load. The wheels are even deeper than they were before. I hope this robot can get out of that hole it's kind of appeared to dug itself in. As long as all 4 wheels spin with enough power, those big cleats hopefully will be able to get them out of that spot. Oh, they made a they backed up, give themselves some runway, and then went full power and powered through the soft, fluffy stuff. That is not an easy feat. This robot is doing some amazing work. Is this the right solution? Is this the winning solution? We don't know. We can't just look at the pile that this robot drops into the scoring zone. We're also looking at the size of the robot, the weight of the robot. We're looking at the power used by the robot. We're looking at whether they're how much of their run was done fully automated and how much was done manually. We're looking at dust lofting and other things like that. There's so many variables. It is important to look at the pile, the berm, the size of the pile that these robots are creating, but it's also important to not forget that there are a lot of variables, and so the robot that creates the biggest pile is not necessarily guaranteed to be the winner of this competition. 2.5 minutes remain for University of Illinois Chicago's first run. So I think probably two more cycles in 2.5 minutes. Maybe not super aggressive cycles, or maybe just one super aggressive cycle. That one seems to have kind of stalled. They're not really making any forward progress. I think the material their wheels are in right there, it's just too soft. It's too fluffy. And or their chassis bottomed out. It's just providing too much resistance. That's a respectable load. It's just not near as full as a lot of the prior ones. With 1.5 minutes, are they going to have enough time to go back and do this one more time before they run out of time? They can maybe do a real quick light load. We're down to 1 minute 10 for University of Illinois Chicago. And they're going for it. Wait, they got 1 minute left. So this is going to be their last cycle. And they keep going back to that same spot. They lifted up those wheels, so they're going a little bit aggressively anyways. They got 40 seconds left. How much time do they need to lift their bucket, drive over to the deposition site, and deposit? They're down to 25 seconds. Is that enough time? 20. It looks like it's going to be just enough time. These students probably knew exactly how much time they needed. Uh-oh. Unless they get stuck. Don't get stuck. Are they going to make it? 5 seconds left. So these are the last few seconds of this team's run. Let's give University of Illinois Chicago a big round of applause. What an amazing run. If we look at that side camera, we can see all those piles, so many very large piles. That is a lot of material. Even though this team had trouble with their autonomy, we'll see when the scoring is done if that made a difference or not. So that was University of Illinois Chicago. Congratulations. Next up on deck, we have the University of Akron. And then looking ahead, we will likely have a quick award presentation after that, and we will give out the Systems Engineering Award, and then have a lunch break. And then after lunch, we will have the College of DuPage. The last of our 10 finalists will be able to do their first run. And then after that, we will start again from the top of the list and give all 10 of those teams a chance to perform their second run. Our current plan is to get through 4 of the 10 teams' second run this afternoon, and then tomorrow we will be able to get through the other 6 teams' second run, and tomorrow afternoon we will have our award ceremony and crown the grand prize for Lunabotics 2025 finals. So as we watch the student teams working and having some fun, but mostly working in their pits, we will be back soon to see the University of Akron perform their first run of this event. Don't go anywhere. All right, you are watching Lunabotics 2025 Finals, and what we just saw was Team University of Illinois Chicago, and I've been able to get a quick interview with one of the UIC students. What's your name?
My name is Elijah Wilkinson.
Nice to meet you, Elijah. What is your role on the team in general, like throughout the entire school year?
So I'm one of our co-captains. Our team has 2 captains. So I'm one of the co-captains, and I'm also the mechanical lead and systems engineering lead.
Okay. And during that amazing run that we just saw, where were you? What were you doing? What was your job?
I was in the mission control room driving the robot.
Sounds like a pretty important job.
Yeah, definitely an exciting one.
All right. So the results from that run appeared to be amazing.
Yeah.
Really, really big pile of material in the scoring zone. You made a good berm. What are your thoughts? What went right? What went wrong? Are you going to do anything different for your second run?
Yeah, of course. So I'll start off with what went wrong, because if people are watching, they probably saw we didn't really move for the first 7 minutes of our run. And so what happened is we got to the mission control, and we were setting up, and our cameras were pulling too much bandwidth. And so we had to readjust to get below the bandwidth number, because there's a maximum number that you have to be below. And we were too high, so we were trying to turn off some of our cameras, and what we ended up doing, we couldn't figure it out, and we just wanted to get going. So we turned off all of our cameras, and we used one of the arena cameras, which is a point deduction, but just one that we decided, take a 60-point deduction and just start going rather than trying to figure it out. So that was our big issue at the beginning. Other than that, everything else pretty much went right. We did another big thing that went really right that we had some issues with in the past qualifying runs is we have an auto excavate cycle. It doesn't count for autonomy for the autonomy challenge, but just something that's really important for our robot to function really well is for, as we scoop, it to be an autonomous function where I push a button and it drives forward, tilts the scoop into the sand at the right angle, then changes the angle, lifts it up, because it's pretty complicated.
It's a sequence of events. It's not
sequence
just one,
of events.
It's not just one command.
Exactly. And that sequence has been tuned. We tuned it at home in sand, and then we came here, and then at the University of Central Florida in their test pit, we tuned it again. Like we said, we looked at how it responded and tried to tune it to basically the best manual cycle that I could drive it doing. But it's much faster than me. It's much more fluid because it just hits this point and then that point, and the wheels keep going the whole time, whereas I'm much slower. But we've had issues with that braking. Like we use it once and it works great in the qualifiers, and then we try to use it again and it stopped working. There was some issue with our tilt actuator, the feedback not keeping up. But we're able to maybe not fix the issue, but solve the problem. And so we don't have that issue anymore. And so the auto excavate cycle was working perfectly. I only took over manually once when we were digging at a weird angle because of the way that we had dug so many holes. But that worked really well. And I think I'm pretty sure that we also achieved the full cycle autonomy, which is 3 cycles of dig and dump, with hands-free controls. We were like on edge. Like I have my hand over the cancel button in case anything goes wrong, and we were just like, but it was fine. I'm pretty sure got it. The judges don't let us know until after the run for sure. But yeah.
So is there anything you're going to do different on your second run, or are you just going to try and do the same thing over again?
Yeah. I think on our next run, we're going to try to do travel autonomy. That's something we had working at UCF, and we didn't feel confident enough to bring it into this run. But we'd like to try to do travel autonomy, and then also do, attempt full cycle autonomy. And also, we're going to start at the beginning instead of waiting 7 minutes to get going. And I think that's going to allow us to dig even more than we already did.
Assuming any more is going to fit into the scoring zone.
Exactly.
All right.
Well,
congratulations on a really great run, and good luck with your second run later on in this event.
Yeah.
All right.
Very much.
Let's check in on our next team, which is Akron. Akron has started their 10-minute setup time. And so they have their robot in the bin and their students in the control room. And so we'll watch over them as they get their robot ready to run. And again, this is run number 1 for the University of Akron. You're watching NASA's Lunabotics 2025 finals, and you're watching the University of Akron robot trying to drive over a rock. Now they're going to drive around it. So the Akron team is set up in the control center, and they do not have direct line of sight contact with this robot. So they're controlling this robot remotely from our control center. They appear to be driving it with joysticks, so manual control. And they have just entered, they've gotten through the obstacle zone, and they've entered the excavation zone. There are obstacles in the excavation zone, I should mention. You can see the obvious rocks in this view. There's also a pretty deep crater that's kind of in on the left side of the robot, that one of their wheels might actually be in that crater. So the Akron team has come to us with a front loader bucket robot design. Four-wheel skid steer robot with a front loader bucket on the front of the robot. And we're going to see in 30 minutes how much material they're able to scoop up and deposit into the construction zone or the scoring zone of our arena. University of Akron is from Ohio. I wasn't sure. I had to look it up. Sorry for my lack of geology skills. So Akron, Ohio, not too far from Cleveland, it turns out. So the Akron, Ohio team nicknames are the Zips, and so their mascot is Zippy the Kangaroo. This Akron robot does appear to have possibly a depth camera mounted on its arm, or a laser scanner. It says Velodyne. I think it's probably a depth camera. So even though they don't appear to be running autonomous right now, they may actually try that in their second run later on in the week. Meaning tomorrow. It's not uncommon for student teams to take fewer risks during their first run in order to try and guarantee at least some points, and then take more risks in their second run. This is a four-wheel drive skid steer robot, similar to a lot of the other robots we've seen in the top 10. We have seen a variety of different wheel designs, wheel diameters, grouser designs. You can see how hard this robot is pushing its bucket into this this tough material. Oh, it seems like it has almost buried itself. All 4 wheels right now appear to be free spinning and not being productive. This is actually surprisingly easy to do in this material. If you fluidize the soil with your wheels, you can sink in, and if you sink in to a point where your chassis is resting on the soil and your wheels basically lose productivity, this can happen. Let's watch this team try and get their robot out of this hole, which they should be able to do with their front loader bucket, hopefully. 23 minutes remain in this run, this first run for Akron. Here's another angle. From this angle, we can see the path that this robot has already traversed several times and the loads that this robot has already deposited into the scoring zone. It also gives us a lower angle at seeing how deeply the wheels are beneath the surface. We talked earlier about all the different design trade-offs that these students have to decide on and trade off. Obviously, all teams are trying to. There, they got themselves out. We're getting some encouragement from the crowd, from the other teams. One of the design trade-offs for the students is size and weight of the robot, as we discussed earlier. Since the final score involves dividing the berm size by the mass of the robot and dividing the berm size by the power used, it is advantageous, or it can be advantageous for a team to create a smaller robot that can still do the job. But sometimes part of that trade is if you make your robot smaller, maybe the wheels end up being smaller and maybe your ground clearance ends up being smaller. So this particular robot doesn't have as much ground clearance underneath the chassis that other robots have, so they're going to have to be careful not to dig themselves down to that chassis with their wheels. So normally you don't think of the wheels as digging implements on a robot, but in this competition your wheels can definitely dig themselves in if things aren't going exactly as you'd planned. So the trick is to get a good bucket load without spinning all your wheels and getting the wheels buried in the quicksand, so to speak. This team did a great job of pulling themselves out of that quicksand just then. And they are continuing to add more and more material to the scoring zone. and almost 20 minutes left in this run. So plenty of time for this University of Akron team to maximize their scoring potential.
Announcement in the pits. The food trucks are here. They're in the southwest corner of the parking lot, right next to this building. And today we have gal-mounted chicken and space crust hot dog.
That is a lot of material in the bucket there. That's impressive. Their front-loading bucket is nearly full right now. That was a very productive cycle right there. Getting a pretty good view here of their mechanical linkages on their arm on the front of their robot. The trick is to get the angle right on that bucket so it doesn't go too deep and it doesn't go too shallow. It's not trivial. It's not trivial to dig with a bucket like this, and especially in this tough material. All right, if these Akron students continue doing what they've been doing over the last 10 minutes or so for another 16 minutes, I think they will be happy with the amount of material they have in the scoring zone. They're making good progress. One bite at a time. Some of that material just then fell outside the scoring zone. I want to remind the viewers the scoring zone isn't this entire corner where the chalk lines are. The scoring zone is just the portion that is between these orange and white posts. So it's important for all these teams to make sure they deposit the material inside those posts. This crushed volcanic rock that makes up the lunar soil simulant in our Artemis arena is actually heavier than it looks. It's heavier than the brain wants you to think it is. So when this robot gets a completely full, maybe even overflowing bucket full, it appears that they they're not going to have a balance problem even if they get a full bucket. They've got enough weight distributed on the back of the robot to keep the robot from tipping forward even with a full load of this dense material. This Akron team appears to be focusing their digging on an area that's just inside the digging zone. The upper left quadrant of the screen is the excavation or digging zone. And so as long as they dig to the left of that fluorescent orange chalk line that is on the ground, that is scoreable material. So by digging close to that line, they're able to minimize their driving time, which could end up helping increase their score versus digging farther away. It looks like they're either picking a slightly offset digging spot or a slightly offset deposition spot. You don't necessarily want to dig in the exact same spot for the entire 30 minutes. You might end up digging yourself into a hole that is hard to get out of. These skid steer robots, when they turn, the wheels have to slide across the surface, and so it's important to consider that in your wheel design. You'll notice these wheels are basically hollow on the inside, and so when they are, kind of drove up on a rock there, when they are slipping sideways, the hollowness of the wheels allows that material not to build up and basically stop them. Okay, I noticed that they didn't dig in the exact same spot. They're actually digging a little bit on the uphill side, which is probably a good plan. Otherwise, they might dig themselves into a deep hole, which we've actually seen other teams do that, and it caused them issues. So this Akron team basically has two decent-sized rocks, one on either side of the robot, that they're staying in between. There's another spot on the left, lower left of the screen, that they could move to if they ended up getting into trouble in this spot. But this team decided not to try and move those rocks as other teams have tried to do in earlier runs. Some teams have a big enough and powerful enough robot that they can just push or pick up and move rocks out of their way. Some teams live with the rocks and dig around them. And both solutions are valid. And honestly, NASA might actually use the results of this competition to help decide whether whether it's going to be important on the moon to move rocks out of the way or just to dig around them. It's really interesting, the data that NASA gets out of running this competition every year and some of the decisions that we could potentially make based on studying the results of this competition every year and studying the actual videos that we're compiling right now of all of these robots interacting with this lunar simulant. They're definitely picking a new digging spot. That seems like a precarious position, at least for one of the wheels. There's a crater that the left front wheel is in right now. Looks like they'll start digging a little bit beyond that crater. When the mission started, for all teams. When the mission starts, they need to get past an obstacle field that has rocks and craters. But then when they get to the excavation zone, it turns out there are also rocks and craters in the excavation zone. So I was just saying how this robot didn't tip forward when it had a full bucket, and there it just happened. I bet that their chassis was already facing down a little bit, which took their center of gravity just past the point. But by putting rocks and craters also in the excavation zone, it makes this competition more realistic and more like an actual lunar mission that we will encounter someday. Oh, as soon as the back end of that robot goes a little bit uphill, it tips over. So it was balanced. it's balanced well when it's on level ground, but the students are finding out, possibly for the first time, that if this robot has a full bucket and is tipped forward by just a crater or by just the level of the ground, that they have a tipping issue. So they dumped a little bit out, and they're keeping the bucket low and trying to get back on stable ground. 8 minutes remain in this run for Akron. And there you can see the material that they've deposited already. And they continue to add to that pile. The theory is that on the moon, this pile of material would be a berm that could be a protective measure for lunar equipment. Could also be raw material that could be used for other construction processes on the moon. On Earth, we use raw materials like sand and gravel to make concrete for our construction projects, and similarly on the moon, we could use this lunar soil as one of the base products in a recipe for a lunar cement, a lunar concrete. The Akron students in the mission control room that are controlling this robot. By the way, they're driving it manually with a joystick from what it looks like. Are very calm, very collected, very serious. And they are just operating this robot over and over in this loop in order to try to maximize the amount of material delivered and deposited into that scoring zone. You can see the student who's driving with the joystick is staring intently into the large monitor. That large monitor has a camera that we're providing. The other student is controlling that camera to make sure the driver is able to see what they need to see. This team has a couple laptops, and you can actually see live camera views on their laptops that are streaming directly from the robot. So these students have several camera views to watch while they're operating their robot. If you go back to the control room, you can see the laptop on the right, which is the student team's laptop. Both of the laptops on the screen are the student laptops, but the laptop on the right, we can actually see their camera. Can we go to the mission control room again, where we were looking at their laptop screen? And as soon as we cut to it, it froze up. They're trying to refresh their camera, possibly. All right, it's not there anymore. You can go back to the robot. Three minutes left for University of Akron. You can see not all that material falls out. They had to take multiple dump maneuvers of their dump bucket before all that material fell out. As we stated earlier, this material is small particles. Particles are very jagged. They kind of stick together, and makes it hard to dig, and also can sometimes make it hard to deposit the material in its final location. Two minutes left for University of Akron, and they've made a nice pile here in the last 30 minutes. Let's try one more time to look at the student's laptop in the control room. Looks like there's two. No, there's one camera view. There's a live camera from the robot as they are backing up their robot. Now they're done backing up. Now they're lowering, so you can see the ground more. Camera seems to be a little pixelated right there, but you could definitely see the ground. You can see the bucket. So they got a really good view of their bucket pushing into the ground right there from their onboard camera view. Now they're about to lift up their bucket, and you'll be able to see the deposit area as that camera lifts up. So this team has a decent view from their onboard camera, but you'll notice the driver is not blinking, not taking his eye away from that camera that we are supplying, which is more of a diagonal view, kind of like what we're seeing here. 40 seconds remain in this run for University of Akron. I think these students are going to be happy with this run. Their score is going to be dependent on the amount of material that they brought divided by the weight of the robot, and also divided by the power used by the robot. So if the weight of the robot is small and the power used by the robot is small, and if the weight of their competing robots is large and the power used by the competing robots is large, could cancel out a little bit. All right. So as time runs out for University of Akron, let's give University of Akron a big round of applause for an amazing run. They should be proud of that run. Looking at the schedule, it is now time. Everybody in the room, It is now time to break for lunch. But before we break for lunch, we are going to have a quick award ceremony. We're going to give away the Systems Engineering Award. You do not want to miss that. So all teams, if you would please come down to the stage end of the room, and in just a few minutes, we will give out the Systems Engineering Award, and then we will have a lunch break, and then after lunch, we will run the College of DuPage. The last of our 10 finalist teams will get to do their very first run, and then after that, we will start over again from the top and give all 10 of our teams a chance to perform their second run. So also for those watching online, we will broadcast our award ceremony, so don't go away. Give us just a few minutes to set up for the award ceremony, and continue watching, and you'll be able to see which team wins the Systems Engineering Award. Don't go anywhere. We will be right back from broadcasting live from Kennedy Space Center Visitor Complex. This is NASA's Lunabotics 2025 Finals Competition. Nobody saw that, right? Is this on? Check, check. Hello. Can everybody hear me? We are about to start a very quick award ceremony. So, as Rob Mueller reminded us at the Lunabotics opening ceremony at UCF, Lunabotics is a systems engineering competition. Even on the award plaque for the Lunabotics SE judges, which is attached to the arena, literally the wall that is the arena wall, it's out there in the hallway. If you haven't seen it, go look at it. It is amazing. According to that plaque, Lunabotics has been recognized by NASA's Office of the Chief Engineer as inspiring more students in the practice of systems engineering than anything else NASA has done. The awards for Lunabotics Systems Engineering paper are some of the most coveted in this competition, and deservedly so. Here's Jeanette Stecklin, Lunabotics Systems Engineering Judge, to present the Systems Engineering Paper Awards.
Thank you, Kurt. Congratulations to all the teams. Your system engineering paper were the best we've ever seen. 38 teams submitted system engineering papers. 19 of them advanced from round 0 to round 1. 5 teams advanced to round 2, the final round for our judging of the system engineering papers. So I'm going to start our awards with the NOVA Awards. The NOVA Awards are given for stellar systems engineering performance by a first-year team. 3 first-year schools made it past round 0, where we usually see first-year schools stay for a couple years. These schools made it past round 0 into round 1 in their very first year. We have 3 awards. The first one goes to Texas A&M University. Now we realize we won't have some of the first-year schools here that didn't advance to the top 10, but luckily we're, I believe, broadcasting the awards this year. So Texas A&M, thank you. The second NOVA Award goes to Boise State University. I believe this is the first year we've had an Idaho team, and Idaho is where I hope to spend my retirement years, so I'm excited to see a team from Idaho. And we have a final NOVA Award. I know this university wasn't able to attend, but I want to give a shout out to Liberty University. Congratulations, we'll have awards that will be sent to you. Now another classic award that I give is the Leaps and Bounds Award. And the Leaps and Bounds Award is awarded for significant improvement over previous years in the application of system engineering to the development of your robot, as demonstrated in your paper. This award goes to a team demonstrating very significant improvement over their previous competitions. If I'm remembering right, 2014 or 2018 is when we first saw them. They spent many years in round 0, and this year they linked from round 0 into round 1, nearly doubling their score from last year. So the Leaps and Bounds Award in System Engineering goes to University of Miami. So if something got into the water in Florida this year, I know Miami won one of our awards from yesterday. We know they're not here, but we appreciate their focus on the competition. So this year, I told you we had just the best papers. I mean, the number of people vying to get into round 2 was tremendous. I would have loved to put 10, 11 papers into round 2, but that requires my judging panel to review every single one of those papers all at once. So we limit how many can go into round 2. But we saw such amazing performance, and you will notice how tightly packed the scores on the top half of the papers are. So this year, we also noticed some very strong performance in each of the system engineering merit elements. So we decided to give special judges award this year. We're going to give a special judge award in a system engineering merit element that we actually requested and required you to talk on, and we're going to give a special judge award this year on a system engineering process or artifact or tool that a team used that we didn't require you to use, but it was an excellent use of system engineering. So we have 2 of these awards. For best use of a required system engineering merit element, this team demonstrated a sophisticated and mature review and control gate process that would be effective for any NASA project to use. To manage their review process, they created a key decision point board that would disposition the comments they received from their external reviewers. The key decision point board took ownership and accountability for the team's decisions on how to respond to external reviewer comments, whether to implement, modify, or reject them. This resulted in the reviews becoming true and effective control gates, getting useful comments to accelerate their system design process. The award for best use of reviews as control gate goes to the University of Alabama. Photographer.
Where do you want us to stand?
Yeah. Yeah, everybody. You need to help direct us with the
2 rows.
Good. Excellent. Thank you, guys. Okay, and now for best use of a system engineering process that we did not specifically require or ask you to provide, and you know you can't ever get in the winner's circle unless you get bonus points, so we have room for that in our scoring. This team did a phenomenal job specifying their interfaces using functional block diagrams. It's not what they called them, but that's what we called them. The award for best use of an SE tool goes to University of Utah.
Joseph.
Joseph.
And Willow.
A couple rows.
Take it.
Yeah, there we go. This is great. And if we don't, honestly, guys.
And fill in right here. Kneel down.
Very packed. I'll block
the squat.
Make sure the stage isn't cramped too much.
He's going to help us with the...
We got to squat more. Squat more. There you go. There you go. Squat more. Squat more.
No, we don't want behind the...
Oh. Dominic.
Come on, you can squat over here.
Should I come over there? This is awesome. Okay.
Move forward.
Got to fit everyone.
Is that good?
All right, we good? Switch places. Long and neat.
There you go. Look at the camera.
Okay. Look, smile. Come on. look at Connor.
Good job, guys.
Good, good.
We're going to end up with, fancy plaques and all, but those are going to the super special local engraver. In the meantime, we have something pretty to show in the photo. Okay. Special Judges Award. And now, drum roll. Yes, thank you, thank you, thank you. And now, the award for the top 3 system engineering papers. For third place winner, the judges had this to say: clear incorporation of system engineering and project management practices and the best organized paper of them all. Outstanding paper flow and use of tables and figures. So as a side, I'll say, if you've gone to our SE seminars this year, we're trying to get across that you can do excellent system engineering and it will help you get a better robot that performs better. So you already win there. But to win the awards in system engineering paper, you have to convince a panel of NASA system engineering and NASA community system engineering judges that you understood it, that you applied it. And so there's some clear communication there. These guys did a super job of that. Additionally, the judges had this to say: excellent use of hierarchy to support discussion, covering what changed from last year, as well as how it and their project evolved over the time. The third place winner for the System Engineering Paper Award is College of DuPage. College of DuPage. They're still representing the 2-year community college. We really appreciate that. Okay. And now for second. For the second place winner, the judges had this to say: extremely well demonstrated use of systems engineering throughout the paper. Outstanding justification of TPMs and driving requirements focused through analysis. One judge said, what stood out for me was their excellent incorporation of the external requirements for the test arena. They carried 3 designs in parallel and off-ramped at appropriate times with sound decision-making based on systems engineering fundamentals. Second place is awarded to University of Virginia. Yeah. today. The first place team. About the winner, this is what the judges had to say. A professional level effort. Particularly mature schedule and budget management approach presented with a range of strategies used to help ensure project success. They had a surprising amount of overall integration of systems engineering artifacts across the board. Everything was related to everything nicely and properly. They planned reviews for the entire life cycle, including a decommissioning review, showing they understood this process was not finished at the competition or the operational phase, as I would call it, just like a real-world project. And you know who you are? The winner of the System Engineering Paper Award is Colorado School of Mines. These are the guys. Okay, intro in their paper. We were always known for making really good robots that perform really well, but we want to get the big prize this year. So we'll pay attention to systems engineering a little bit this time. Super job, guys. Oh my God!
I'm gonna cry. Picture? Am I hiding someone?
We can move all this way.
Oh, okay. Oh my God.
Thank you, everyone.
That concludes our mini award ceremony. Now go have lunch and prepare for the next runs. We will announce the next runs online and in the room when the schedule comes to light. Don't go anywhere, everybody who's watching online. We will be back after a quick lunch break. In the meantime, enjoy these awesome NASA videos and live stream or live views from around this building. Don't go anywhere, we'll be back. You're watching NASA's Lunabotics 2025 Finals event. See you, we will be back soon.
The space station is a great platform to test not only the hardware but the operations of living and working in space. The beauty of the space station is that if something goes wrong, we can get ourselves safely back to Earth in pretty short order. We don't have that luxury when we go to deep space, so this is the place where we make sure we've got it all right before we send our friends and colleagues out into deep space. I think the most important thing we've learned while living and working on the space station is that we can only do it when we're all on the same page. We work with different people, different cultures, different nations, and it is amazing to see what we can accomplish when that machine is firing on all cylinders. And we do it every day, and we've been doing it for decades. Nobody does this alone. Human spaceflight is a team sport, and without the hundreds of thousands of people who are supporting it, we would never be able to do it.
The ISS is the most incredible wonder of the modern world. NASA's learned a lot of things from the ISS program, both fundamental biological and physical sciences, but also exploration. The single greatest achievement that I feel that the ISS program has produced is that we can grow crops normally off Earth. My favorite memory of ISS support is Scott Kelly did a bouquet from the zinnias. He created the first ever off-Earth flower arrangement. What I hope to see from the ISS as we move forward is more tests of sustainable technologies and approaches like crop production.
We've laid a foundation and an experience base across NASA and across the globe that's going to serve
us very well as we move into exploration, both in low Earth orbit as we continue, but also for Moon and to Mars. Human spaceflight is really complicated and it's really unforgiving. Assembling space station was really complicated, yet we successfully did that in space, on orbit, and created the most advanced and complex spacecraft that's ever been built. We have spurred a commercial interest, we've spurred a government interest. There's a passion for space that didn't exist before. I think that inspiration, that motivation that we generated across the globe is probably the single most astounding accomplishment that we've had with the space station.
From the ISS program, NASA's learned really what happens to the human body in zero-G over long-duration flights. When we go to Mars, we'll be committing those people to a long-duration mission, so it's imperative that we know what that's going to do to their bodies. You know, I think the greatest thing the ISS has taught us is really that you need to be flexible and modular. We've moved modules around on the ISS, we've moved docking ports around. I wish everybody understood that the ISS requires a large team of people that are looking at millions of pieces of data every day. It's a very detail-oriented operation. So my best memory of ISS support is actually a personal memory. I met my wife there. We were both flight controllers. We met in MCC, and actually I proposed to her in the flight control room. As the ISS moves forward, I hope to see it continue as a zero-G laboratory. I hope to see it as a test bed for long-duration deep space missions so we can test out new hardware and designs.
My best memories are the stressful ones, but when we've had things that have gone wrong on space station that needed to be fixed quickly, just watching the teams, the leaders, the engineers, the safety folks, the health and performance folks all come together very quickly, sacrifice time with their families, work 24 hours a day until that problem was fixed and solved. It's just amazing watching the people come together to keep this thing working. NASA has learned so much from the ISS program. It's amazing. Everything from how to live in space for long periods of time. And for me, from the engineering side, what we've really learned is how do you keep a really, really complex machine working continuously? Those are questions that we need to answer to make it to Mars, to far-off destinations, and the space station has been really important for helping us get there.
NASA has learned so much from the ISS program. That collaboration across different countries with a common goal has been significant. Since we started building this project here at the Kennedy Space Center, we had to assemble all the components and test the systems to make sure that they will work here as they were intended. When I originally started, ISS was only supposed to be 15 years. Now we're at 25 years. So being able to see that still in space, and now I'm launching astronauts that are going to ISS to be living in those modules that I help test and integrate here on the ground is extremely rewarding. As ISS continues its mission, I hope that we see a lot of more breakthroughs in research. So I hope that all the different testing is going to enable us when we go to the Moon and to Mars to better understand how the human body will endure during those long duration missions.
In terms of the next decade of space station operations, I really think we can continue to take advantage of the tremendous laboratory. We continue to learn more about material science, human research, help position ourselves for exploration. I think space station's an excellent test bed for exploration. We've done numerous things on space station to test exploration ops. It's a series of habitats that you have to keep sustained, and then you have to integrate those science operations for multiple crews. And so it's a good surrogate for a lunar base or even a Mars base someday. It's just an incredible facility, and the fact that we've had between 2 and 6 astronauts in orbit continuously for 23 years and how challenging that is. We have an incredibly dedicated, talented team, and they are there to make the flight successful and make them safe. And I see that every day, and I'm just proud to be a part of the team.
Christina Cook of NASA, the first one through the hatch, being greeted by her crewmates aboard the International Space Station.
The one thing I wish everyone knew about the space station was really that we've had astronauts off the planet for 23 years continuously. That to me is just incredible. The greatest single thing that we've learned on the space station is to grow and eat our food. When we're on Mars and we're growing and eating our food on Mars, we're going to trace that all the way back to the space station. Well, the astronauts grew and ate the red romaine lettuce on space station. It was Scott Kelly, Kjell Lindgren, and Kimia Yui. Kjell harvested the lettuce, and then they shared the lettuce, and they did a cheers. They toasted the lettuce and ate it. Another really great memory of space station was when Scott Kelly unbuckled the zinnia flower that he grew. It was really fun to see him take it out to the cupola. I hope to see continuously produced crops on space station for deep space exploration missions.
I think folks don't realize that it takes an army of folks and a huge effort to safely operate the ISS and make sure that we can continue to do the work that we do and to provide those science and research activities. I think that NASA has made something very hard look very, very easy. I don't think the general public realizes the behind the scenes that goes into making that such a success and really giving all those teams of people, you know, the accolades that they deserve. We've learned so much about international cooperation. I mean, the ISS has been successful because of the international partnerships we've had. We've learned the importance of that both in developing technologies, collaborating on science, but also in terms of foreign policy and national interest.
NASA has learned a tremendous amount from the International Space Station, not only from a technological perspective, but from a human side as well. The ISS is a marvelous technological platform for science. But what we have learned as an international community, crossing cultural differences, political differences, to support the men and women who are willing to go into space for exploration and science on behalf of all humankind, I think is one of the legacies that we're going to have. When you go outside at sunset or early in the morning and you track the ISS coming over your locale, realizing there are human heartbeats on board going at 5 miles per second. It's very special to realize that they are our friends, their families are important to us, and we do everything we can to maintain all the best of their health and well-being.
I get to help the astronauts launch and return from the International Space Station. There's been a lot of learning happening over the last couple of years, 25 years now. I wish that everyone would know that the space station is one of the biggest international collaborations that NASA has. I think it is the foundation and testbed of just humanity's effort in space. The first ever flown in space object I got to touch was from working on ISS. Advanced Plant Habitat did an amazing thing where they flew some patches for us on station and returned them for the team that worked on the Advanced Plant Habitat project. So as someone who grew up loving space and wanting to work at NASA for more or less my entire life, that was a pretty impressive memory and remains something that I hold very dear. Moving forward, I hope to see more experiments, more of the science that gives us perspective on the human body and the workings in a zero-gravity environment, which will allow us to understand a microgravity environment like the moon or on Mars.
It's the only place in the world that we can do microgravity research. Think about that. One place in the whole world. There are no chambers on Earth where we can replicate microgravity, just the space station. So we have to use that in order to figure out what we need to do for exploration. The first thing we learned is what we didn't know, right? The questions we needed to ask. Moving from shuttle to space station, going from short duration to long duration, we discovered many, many things that we didn't even know were risks of spaceflight. But we can use a space station as a space analog for other space destinations. So that's really where we're going to focus, is how do we get to the moon safely? How do we get to Mars safely? Space station will allow us to do that.
International partnering, international cooperation, engaging research, those three things to me are one of the most important things that the ISS has provided. You know, when we embarked in processing the elements of the ISS, nobody knew how to do it. We kind of figured that out as we were going through it. One thing that everyone should know about the ISS is that it's a great platform to do research, and that we need that platform and future platforms to help us understand how we're ever going to be able to go even farther out into deep space.
in terms of what I want to see, I think the continued amazing science that the ISS provides, a little bit of what they have provided to humanity is going to pay big dividends down the road. The deep space explorers that go beyond low Earth orbit, they're going to take a lot of things from the ISS. The ability to do things autonomously by themselves without the ground helping them is going to be one of the key things that the ISS provides. The one thing that I hope people realize about the International Space Station is that it is not just America's, that it's humanity's. We're not just doing things for the benefit of the United States. It's just bigger than what we are.
Every new day for us now is a record until you come home. Thanks for that.
The space station is a platform for bigger and more complicated exploration. The greatest achievement of the space station is collaboration. To work together, countries come together, and once we are on board of the space station, living there in the case of the astronauts, we are all the same. It belongs to humankind. It belongs to all the nations that have collaborated and built this station, and furthermore, it belongs to all humans because of what we are researching and discovering for a better life on Earth.
I wish everyone knew that the space station is just a technological marvel designed by engineers all over the world. I think the ISS has a lot to offer for deep space explorers. It's helping us learn how to design and operate systems to keep humans alive. One day that stands out to me is when we launched Crew 1. I was the mission manager for that mission, and it was just an incredible achievement to finally be providing crew transportation services to ISS, which is the whole reason that commercial crew program exists. I think the most important thing we've learned through the ISS program is the great things that we can achieve as really a human species if we work together.
Happy 25 years to the International Space Station.
Happy birthday, ISS.
Happy 25 years, International Space Station.
Happy 25th, ISS.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
Happy 25 years to the International Space Station.
Happy 25th, ISS.
Happy 25 years, International Space Station.
Happy 25th birthday, International Space Station.
Happy 25th anniversary, ISS.
Happy 25th anniversary, ISS.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
We can't wait to see what's next for the space station.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
Go. Prop. Go. TDA. Go. FIDO. Go. All right, so go for launch.
Our destiny is always to go and see what's further and what's next.
FIDO. Nominal main flight. Copy.
NASA is preparing for a journey back to the moon, and after that, we're setting our sights on Mars. To get there, we need tons of rocket power coming from our Space Launch System.
When it comes to how much power this thing can push out, this thing is massive.
It's going to be mesmerizing to stand next to this massive vehicle. The immensity of it, knowing that this thing is going to be propelling a rocket into space and around the moon.
Hang on, it's probably best to start back at the beginning. It all started in Promontory, Utah, where Northrop Grumman manufactured each of the segments that make up the rocket's boosters. After a 10-day cross-country journey, the booster segments were delivered to Kennedy Space Center's Rotation, Processing, and Surge Facility, or RPSF. If this all sounds familiar, that's because it's the same facility that was used to process shuttle booster segments, which all came from Utah. Then they're ready to go to the iconic Vehicle Assembly Building, or VAB, where the rest of the motor segments are assembled and stacked on top of the mobile launcher.
So the one thing about this vehicle, of course, it's produced all across the country. Components all come here. They may be built around the country, but they all come together right here in the Vehicle Assembly Building.
Our SLS rocket will generate 8.8 million pounds of thrust to break through Earth's gravitational pull. That's more power than the Space Shuttle and the Saturn V rocket used. Teams with NASA's Exploration Ground Systems are responsible for assembling the boosters that will house the majority of that power. The twin solid rocket boosters, made up of 10 total motor segments, will stand nearly 17 stories when fully stacked. First, teams will inspect and prep the hardware. Next, they're ready to start stacking the segments, a process that takes time, patience, and a steady hand.
Once we have everything done in High Bay 4, we pick up the segment with the 325 crane, pick it up over the 16th floor crossover to where you see it now, and we begin stacking the segments. Each segment, we lift over the 16th floor crossover and stack it. Once we stack it, we put it on top of the segment below, and we put about 177 pins all the way around the whole thing to attach each segment.
And the pressure to perform the operation flawlessly can test the team's nerves.
There's a tremendous responsibility involved with processing flight hardware like this. It's nerve-wracking at times, but it's exciting. There's zero appetite for risk in a program like this.
We have a bunch of shuttle guys that are here to show us along the way. You know, if we get stuck, they're there to guide us. At the beginning of the stacking, it was very nerve-wracking. You know, with each segment that we stacked, a little bit of the nerve comes off. By the third or fourth one, it's easy peasy. You know, we're pushing through, all the jitters are gone, and we're just excited to get finished with it.
With all 10 booster segments now fully stacked on the mobile launcher, there's just one final piece of the puzzle to round out the power needed to get SLS off the ground and send it to space. Core stage. After a 900-mile journey aboard NASA's Pegasus barge, the SLS core stage, the largest rocket stage NASA has ever built, has made it to Kennedy Space Center.
Today is a huge day. This is the last piece of big hardware that we need for Artemis 1 processing. And we've just been waiting a long time for this part of the vehicle to arrive so that we can get going on the next steps of our stacking operations.
Standing an impressive 212 feet tall and weighing a whopping 188,000 pounds, the core stage came all the way from Stennis Space Center in Mississippi. The core stage went through round after round of rigorous testing, including what's called its Green Run series, truly putting its performance to the test. The series involved 8 rounds that looked at systems individually before culminating in pure power. With over 700,000 gallons of propellant flowing through the core stage and its RS-25 engines firing for 8 minutes straight, the successful final test resulted in some big emotions from the team.
We cried, we laughed, and we cheered because it was so emotional to see, the years of culmination coming through.
And that victory did not come without overcoming a few challenges, proving why at NASA we test as frequently and as hard as we do.
And we got to shut down. All personnel.
So we actually did a 1-minute test on the first hot fire test. And then we learned a lot from that. We understood the vehicle more, we made a few changes, and then we got back into our second hot fire test.
There was a lot of joy and workmanship and ownership of being able to work that process and be able to get it done. When we went for the second hot fire and we went for the 500 seconds, that was just pure exhilaration.
Following its arrival at Kennedy, teams moved the core stage into the VAB, where it was lifted by a crane and placed in between the twin solid rocket boosters. Serving as the backbone of the rocket, the core stage will provide more than 2 million pounds of thrust to help send the Orion spacecraft on its trip around the moon.
Essentially, we have these 2 massive cranes that are located inside of the VAB, where we go ahead and we pick 2 points at the end of the core stage, one on the back portion of it and on the front portion of it. We lift it up to the point where we're able to transition it from a horizontal position over into a vertical position, and then essentially bring it way up to the top of the vehicle assembly building and cross it over into high bay 3, in which we ensure that we don't damage any part of the vehicle as it's incoming into its position.
NASA's largest rocket stage, now fully integrated with the twin boosters, is ready to get Orion off the Earth. But it will take one more critical component to give the capsule that extra push it needs to journey tens of thousands of miles beyond the moon. With just a single RL-10 engine, the Interim Cryogenic Propulsion Stage, or ICPS, will provide over 20,000 pounds of thrust to send Orion on the ride of a lifetime. To connect the ICPS with the rocket stack, teams next added the launch vehicle stage adapter to the core stage, followed by the ICPS.
The ICPS is the Interim Cryogenic Propulsion Stage, and essentially it's somewhat of the upper stage of the entire SLS vehicle. And what that will do is propel the Orion capsule along with its service module over to its destination, which at this point in time will be the moon.
But before the spacecraft can be attached to the rocket, teams will conduct a series of tests to ensure all of SLS's components communicate properly with one another, plus the ground systems equipment, the launch control systems, and its software. Adding to the challenge, those methods for testing have changed significantly since the days of the Apollo program. Initially built in the 1960s to house assembly of the Saturn V, the VAB has undergone some major modifications to support several different kinds of rockets and spacecraft, whether they're going into low Earth orbit or venturing to deep space.
This high bay was Shuttle Heritage. Before that, it was Apollo Heritage. So there's upgrades that are still occurring today to include upgrades that will support Artemis 2 and Artemis 3.
When SLS blasts off from Kennedy's Launch Pad 39B, Orion isn't the only thing it will be sending to space. Hitching a ride with Orion are tiny shoebox-sized satellites called CubeSats that were loaded into the Orion stage adapter in Kennedy's Space Station Processing Facility. The extra room in the stage adapter provides a rare opportunity to send those CubeSats to deep space to conduct science and research of their own. And these CubeSats are on tap to study a range of topics, from the moon to asteroids to the effect of space radiation on living organisms. At this point, the stack is nearly complete. All that's missing is the spacecraft itself, which has been in the Launch Abort System facility, getting outfitted with one of the spacecraft's most crucial pieces.
The Launch Abort System is kind of that pointy solid rocket motor that's at the top of Orion, and it's there to protect the crew in the event of an emergency, so it's a very important system.
Fully integrated with its Launch Abort System, the Orion spacecraft slowly makes its way to the VAB in the overnight hours. Upon its arrival, teams carefully lift and lower it onto the Orion stage adapter. With this operation, stacking the most powerful rocket the world has ever seen is complete. And what a sight to behold.
We're trying to decide, what does exploration look like in the future when we retire shuttle? You know, what does our nation want to do? Where do we want to go? How do we want to explore? To see it go from those days of words and ideas in people's heads to the 3 programs we have today and the Artemis mission and all the hardware that's been produced in factories ranging from big aerospace companies to little mom and pop shops all over the country and the world. It's unbelievable, and I'm just really proud.
Before SLS and Orion can launch our nation into a new era of space exploration, a series of tests needs to take place inside the VAB, validating the rocket and spacecraft as an integrated system and paving the way for one final milestone: wet dress rehearsal. The 322-foot-tall, fully integrated rocket will roll out to Launch Pad 39B for a full test, allowing the launch team to run through a full launch countdown, but stopping just short of firing the engines.
I think we're going to be so proud when it rolls out of the VAB. I will personally be probably crying a little bit because it's such a big event. We worked so hard to get us to the day of rolling out. I'm probably going to be bawling when we launch it. See it through my tears because it's just a culmination of so much work from everybody.
We owe the advancement of science and research and technology to what we're doing here, and this is a big opportunity for us as a nation to reclaim our spot at the forefront of human space flight and exploration.
Artemis is going to be a major part of history. It most definitely is going to rock the space industry when it flies. This program is going to go to the moon. It's going to go to Mars. We need that. This country needs that. This world needs that.
I'm so excited. It's going to be a lot of work ahead of us, but Artemis 1 is going to surprise everybody.
What an exciting day at the Kennedy Space Center. You can see the Orion spaceship coming out of the ONC building where we've been assembling it for several years. As big a step as this is for us today in rolling out and starting the journey of Artemis 1 to the moon and beyond, we're really excited for this test program to get this vehicle flowing and to begin the next steps, which are to send humans back to the moon.
The twin sister of Apollo, Artemis is the name given to the program that will return humanity to the moon. And named after one of the largest constellations in the sky, Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the O&C building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the O&C. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the O&C's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up, and then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
All the people, the work, the components that have gone into this vehicle, it's just an amazing feat.
Teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives, from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis 1.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European Service Module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
It really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. It hits you in the heart, and it really speaks to why we all are doing what we're doing.
I never thought as a little kid growing up I'd be part of something like this today. Now as a dad of two young girls, to be able to tell them what I do and to be able to have them someday watch the first woman stand on the moon is pretty amazing to me personally.
As the Orion spacecraft departs the ONC, its next stop is the Multi-Payload Processing Facility, or MPPF, where teams with NASA's Exploration Ground Systems and prime contractor Jacobs will perform the next set of milestones, fueling and servicing the spacecraft.
We have a few months of hard but rewarding work ahead of us to get to launch, but this is it. This is our year. This is our time and what folks have worked so hard for.
Now we're going to continue with processing, get that thing checked out, fueled, get the launch abort motor stuck on top of it.
With fueling of Orion's crew and service modules complete, the spacecraft moves from the MPPF into the Launch Abort System facility.
We just finished fueling the spaceship, and we moved it to the LASA facility, the Launch Abort System facility, to put the Launch Abort System on the top of Orion.
And in July 2019, teams completed a critical test, the Ascent Abort 2 flight test, to validate the Launch Abort System works as expected. After reaching an altitude of about 6 miles, where the test spacecraft experienced high-stress conditions expected during launch, the abort sequence triggered. Within milliseconds, the abort motor fired to pull the crew module away to safety. Its attitude control motor flipped the capsule into the proper orientation, and the jettison motor fired to release the crew module for a splashdown in the Atlantic Ocean.
I feel, just honored and humbled every day to be able to work on this stuff.
This rocket is just going to be absolutely amazing.
Now that the spacecraft's launch abort system is securely in place, Orion is ready for the next stop on its path to the pad, the Vehicle Assembly Building. Once inside, the spacecraft will be placed on top of the Space Launch System rocket, the most powerful rocket the world has ever seen.
Across the nation are sacred sites that capture the spirit of America's character. And one of those places is right here, the Kennedy Space Center.
Every single vehicle that has carried humans beyond the bounds of low Earth orbit has undergone integration and testing in that vehicle assembly building, crawled down this roadway and launched right here from the Kennedy Space Center. The Space Launch System, mated with the Orion spacecraft, will continue this proud tradition.
As soon as we roll out of the vehicle assembly building, High Bay 3, and the world gets a chance to see this rocket, I think it is going to be shocking.
On March 17th, NASA took a giant step toward returning humanity to the moon. The fully assembled Space Launch System rocket and Orion spacecraft for the Artemis 1 mission made its debut outside the massive vehicle assembly building.
We've seen the mobile launcher outside, and it's massive, but now add an over 300-foot rocket on top of it, it's just going to be amazing.
Charlie Blackwell Thompson oversees the launch countdown, ultimately providing the go for launch.
Entity, launch director, representing this team and all the men and women that have worked to make this day happen, I proudly give you a go to roll the Artemis launch vehicle to the pad.
Ladies and gentlemen, the world's most powerful rocket right here.
Once outside, the rocket began its nearly 4-mile journey to the pad, riding atop a 6.6 million pound crawler transporter, which was originally constructed to transport the Apollo moon rocket.
In 1 year, we have completely stacked the vehicle. We've completed most of our testing, all very successful, and we are so close to launch, and the excitement is just crazy.
Now NASA's new moon rocket is making the same journey the Saturn V took 50 years ago.
And just as all eyes are on the SLS tonight as it makes its journey, in a few short weeks, all eyes are going to be on the sky as it rocks the space coast and takes its maiden flight around the moon.
It is amazing to see the culmination of all of this work of many years from many industries and many people that have come and go, to have a chance to then now see their work going over to the pad and then launching to go to the moon.
The rocket is rolling to historic Launch Complex 39B, its launch pad used for both Apollo and shuttle launches, sending hundreds of astronauts to space throughout the decades, and now on tap to send hundreds more as we return to the moon and venture beyond to Mars. But for this mission, there will be no astronauts on board. Before the uncrewed Artemis 1 stack can launch to our nearest celestial body, it has to travel to the pad for a wet dress rehearsal, a test to run the rocket, capsule, launch team, and launch pad through their paces, simulating a launch countdown.
When we get to the pad team will be connecting all the interfaces between the pad and the mobile launcher so that we can go ahead and start our operations at the pad. So at that point, the launch director really takes over, and she will go down the sequence as if it was really a normal launch day.
Wet dress rehearsal is essentially launch without a launch. It is to, really the reason we're doing it is to verify and validate all of the pieces that go into launch countdown. So wet dress is really our opportunity to find any issues or adjustments that we need to make in our launch countdown.
For Artemis 1, the wet dress rehearsal is the final and most critical test before the rocket can return to the launch pad for liftoff to the moon. During the countdown, over 730,000 gallons of supercooled liquid propellants will be loaded into the rocket as part of the nearly 2-day launch countdown.
We will configure all of the ground systems exactly the way we would for launch, and we will fully load the core stage and the interim cryopropulsion stage with their liquid fuels. That'll be the first time that that's been done from here at Kennedy Space Center. There have been pieces of these things done in multiple different areas. We've tested all of these systems in multiple different locations, but this will be the first time where we pull it all together and do all of it all in the same progression that we've we've got laid out for launch countdown.
Wet dress is the biggest milestone we have aside from launch, because that means that the rocket is now put together, has been tested separately and together, and it is ready to go and be filled with fuel to simulate how we're going to do it at the pad, and then it tells us the rocket is ready to go for launch.
And behind that wet dress rehearsal is a launch team made up of hundreds of engineers monitoring each system of the 320-foot-tall Artemis 1 rocket and capsule. Sitting in firing room 1 is the core launch control team, monitoring hundreds of launch commit criteria to ensure the ground systems and flight hardware are ready for launch.
Now you would think that launch control team in firing room 1 is it, that's all you need. We have an expansive support team across really the entire NASA enterprise that is supporting us on launch day.
And that support spans the entire nation, from additional systems engineers sitting in Kennedy's Firing Room 2, to the flight control team at Johnson Space Center in Houston, to the contractors responsible for designing and building each segment of the rocket and capsule.
This team is really shaping up to be a great, very skilled and ready to operate and execute launch for Artemis 1.
With the Artemis 1 launch team now fully certified and the wet dress rehearsal complete, SLS and Orion are ready for their final pit stop, returning to the VAB before venturing back to Launch Pad 39B for liftoff.
I mean, we are going and we're going together, and we're having an opportunity to do this in a new generation of space exploration in which I can say that I'm honorably a part of.
You know, you come every day to the VAB and you see the rocket and you can't believe what we have accomplished.
People throughout history have always explored, and you never know what you're going to learn.
Exploration is not always about the destination, but it's the path that you travel, the things you learn along the way.
And the things we're going to learn are going to be incredible. We can't even begin to understand what those are today.
Our workforce has been a relentless spirit. We imagine, we build, we never stop pushing the envelope of what is possible. What President Kennedy said was, we choose to go to the moon and do other things, not because it's easy, but because it's hard.
The cost of failure is much higher than the cost of scrubbing. We have an obligation to get this right.
This is a whole new vehicle, a whole new technology, a whole new purpose of going back to the moon in preparation to go to Mars. And yes, it's hard.
The countdown to T-0 starts approximately 2 days before launch. Teams inside the Launch Control Center have been working around the clock, powering up each section of the rocket and configuring the launch pad to support the 8.8 million pounds of thrust our moon rocket will generate at liftoff.
It is a new creation. It is a new rocket and a new spacecraft to send humans to the moon on the very next flight.
Today, we make history. With the launch of the most powerful rocket the world has ever seen, we are taking the first step in humanity's return to the moon.
I can tell you there's an energy and there's an excitement around the Kennedy Space Center, I would say, across the agency and all around the Space Coast as we get closer and closer to this launch.
This mission will validate that the rocket and capsule do perform as expected before future Artemis missions send astronauts to the lunar surface.
We have worked really hard to get here. The team has done an absolutely outstanding job, and we're up to the challenge, and I'm really looking forward to a successful test flight.
You are looking at the world's most powerful rocket and Orion spacecraft live on Launch Pad 39B. Artemis 1 embodies the hard work of thousands across the world, determined to explore for the benefit of all. I'm Megan Cruz, and this is NASA astronaut Kayla Barron.
When I first walked up and saw the view from the desk here, I was just blown away.
This is the moment when it comes to the countdown, and then tension starts, and well, let's cross fingers, everything works well. Tension is rising, and we are fully excited here.
Over the past few years, teams have put in thousands of hours, performing simulations and rehearsals to ensure that they are ready for this moment.
As our 0 hour approaches for the Artemis generation, we do have a heightened sense of anticipation, and there's definitely excitement amongst the team members. We've noticed just the overall mood and focus within the team is definitely a positive one.
Now, with all systems configured correctly, the launch director gives the final go for liftoff.
On behalf of all the men and women across our great nation who have worked to bring this hardware together.
To make this day possible. And for the Artemis generation, this is for you. At this time, I give you a go to resume count and launch Artemis 1.
This mission goes with a lot of hopes and dreams of a lot of people. It's no longer the Apollo generation. It's the Artemis generation. And that brings a whole new world of discoveries.
T-minus 50 seconds and counting. The Space Launch System is now counting down to liftoff of Orion on its maiden voyage to the moon. And here we go.
10.
Hydrogen burn-off igniters initiated. 7, 6, 5. 4-stage engine start. 3, 2, 1. And liftoff of Artemis 1. We rise together back to the moon and beyond.
Well, if you're just joining us, welcome to NASA's Kennedy Space Center, where we just watched Artemis 1 launch, our first step towards our next adventure into deep space.
With Orion off the ground, Mission Control in Houston takes the reins. Our nation is returning to the moon.
And we have worked hard as a team. You guys have worked hard as a team for this moment. This is your moment.
is not by chance that you are here today. So I want you to look around at this team and know that you have earned it. You have earned your place in the room. You have earned this moment. You have earned your place in history.
The successful launch of SLS is just the beginning. Orion will spend the next several weeks journeying around the moon, sending flight data back to teams here on Earth for real-time analysis. During its mission, Orion reached speeds traveling about 30 times as fast as the speed of sound.
This dramatic video of the Earth-Moon transit that took place showed and punctuated the fact that we were pressing away from our home planet to a distance of some 268,000 miles away from Earth, further than any human-rated spacecraft had ever traveled, for a spacecraft designed to return humans to Earth, eclipsing the mark set by the Apollo 13 vehicle back in 1970.
After several weeks of flight, it was time for Orion to return home.
A half-century later, NASA's newest moon explorer, the Orion spacecraft, is barreling its way back home after circumnavigating the moon and beyond in an elliptical distant retrograde orbit. Now less than 2 hours away from splashing down in the Pacific Ocean west of Baja, California, to complete its shakedown mission.
Like the Apollo missions of the past, Orion will have to endure incredibly high temperatures during re-entry of Earth's atmosphere.
A journey that began with the power of the launch of the Space Launch System 25 and a half days ago, about to reach its final minutes in the searing heat of re-entry, where temperatures around Orion will build up to 5,000 degrees Fahrenheit.
While re-entering Earth's atmosphere, the spacecraft slowed to about 300 miles per hour. As it continued its descent, Orion's parachute system, containing 11 total parachutes, deployed once it reached approximately 9,000 feet and a speed of about 130 miles per hour.
And there it is, high over the Pacific, America's new ticket to ride to the moon and beyond now in view. Orion under its chutes descending toward splashdown.
These parachutes help slow the crew module to a much more manageable speed, roughly 20 miles per hour, for a water landing off the coast of California.
Splashdown. From Tranquility Base to Taurus Littrow to the tranquil waters of the Pacific, the latest chapter of NASA's journey to the moon comes to a close. Orion, back on Earth.
You are watching NASA's Lunabotics 2025 finals live streaming from NASA's Kennedy Space Center Visitor Complex. And we have just recovered from a lunch break, and we have the College of DuPage team at the very end of their 10-minute setup time. And so we are about to see the College of DuPage team perform their first run of 2 official scoring runs here this week. This DuPage team is our final team to run through their to run the robot in their first run. As soon as DuPage is finished, we will start running teams through their second of 2 runs in our event this week. And so as soon as our judging team is ready, they will start the 30-minute timer for College of DuPage's run. And there's their robot. You can see this is a tracked vehicle instead of a wheeled vehicle. Sometimes tracks can give you a lot more traction. There's a lot more surface area that's in contact with the ground in a tracked vehicle, especially a compliant tracked vehicle, one that has maybe some soft rubber that can give you a lot of surface area that is touching the ground. This robot also uses a dozer blade on the front of the robot to push the material. And as long as that dozer blade starts dozing over in the excavation side of our arena, it's allowed to push material all the way from that side of the arena into the scoring zone. Okay, we're 1 minute in. Waiting to see some movement here from this DuPage robot. So we've noticed the DuPage students have been hands-off, so they may have some autonomous software that's running right now. Okay, the student just grabbed the joystick, it looks like. Now we're seeing the robot move finally. It's possible this team was trying to do some autonomy right out of the gate and gave it some time to allow it to work, and then at some point decided, well, let's just go ahead and drive this robot and forfeit those autonomy points. That's a tough trade-off for all of our student teams. Now this robot has gotten through the obstacle part of our arena, and it is now in the excavation or digging part of the arena. And now as long as it puts its blade down inside that square, it's allowed to push material into the scoring zone, which is in the lower right hand side of the screen. This robot appears to be going for that rock, So this is telling. If this robot doesn't look very big compared to some of our other competitors, but the tracks that it uses instead of wheels may give it so much traction that it's able to push this rock out of the excavation zone and possibly into scoring position. There's no rule against putting rocks into the scoring zone. They will count as volume excavated and delivered. They'll have to overcome the rock kind of wanting to dig itself in. They'll have to kind of lift up on it as they push. All right, for a second there, I was worried because it looked like they were a little bit stuck, but they have just gotten out. DuPage has just gotten unstuck, repositioned themselves, possibly ignoring that rock for now in order to get some material into the scoring zone. So they're about roughly in the middle of the excavation zone, and they have lifted their blade. They're moving towards they're moving closer to the scoring zone, and they're pushing their blade down now. So it's looking like they're going to try and start over there a little bit closer to the end goal. All right, that was their first cycle of pushing material into the scoring zone. The scoring zone is between the orange and white posts, but the excavation has to start in the excavation zone, which is on the far side of the fluorescent orange chalk line on the ground. So this team has to trade off how far they push that blade down into the soil. If they push down too hard, their tracks, as much traction as they have, are likely to spin, at least right now where the surface is light and fluffy. The chances of their tracks spinning in place are higher here at the top of the surface. Once they've scraped off a few inches of material, the material underneath will likely be harder, and that's a good bite right there. Although if they take too much of a bite, then they're going to start slipping. So this is the game this team from DuPage is going to have to play, is pushing their blade down just far enough to get a good amount of material, but not too far to the point where their tracks start slipping and not being productive. College of DuPage, I looked it up because I wasn't sure where they were from. They're from Glen Ellen, Illinois, which is a suburb of Chicago. And they are a community college. This is a 2-year community college competing against major 4-year institutions. So really impressive showing by a community college to make it into the top 10 teams in NASA's Lunabotics 2025 finals. This team should feel very proud for making it into the top 10. And hopefully they'll get some good amount of regolith simulant pushed into the scoring zone here in their first run in order to be competitive. You'll notice as more material piles up in front of the robot, it'll have more of the slipping of the track. So this is the, oh, there's a lot of material that is not falling out of that dozer blade. It is stuck there. They're going to have to wiggle it out. These students are operating manually. We can see the students in the control room operating a joystick. We can see the students in the control room watching one of the big monitors in front of them, which is the camera view supplied by NASA, giving them an overhead view. There they go. They got a good amount of material definitely into the scoring zone just then. In this camera view, you can see a pile there on the right side of the screen that they most definitely pushed in there. There's still a lot of simulant stuck in their blade. This is what I've talked about many times about how this material can be sticky. It sticks to itself. And that's just due to the physical nature of these particles being jagged in shape and locking together like puzzle pieces and holding on tight, making it hard to dig and sometimes hard to offload into the scoring zone, it turns out. What we want to see is progress forward without completely lifting up off the surface. So what this team has maybe inadvertently done in the first third of this this run for them is created a little bit of a downhill slope for digging, and then they've lifted their bucket and made a pretty non-trivial uphill slope. And so navigating between the downhill and the uphill while also moving your bucket appropriately to not compound it and make it worse is that's not a trivial task. But with 18 minutes remaining, there's plenty of time for this team from the College of DuPage to either pick a new spot that doesn't have that problem, which looks like what they're doing right now. They've picked a new spot to lower their dozer blade. If that spot is flat, relatively flat, all they have to do is just drive forward and magic happens, which is what you just saw. Now if they continue to keep this run, this track that they just made relatively flat, then it'll be relatively easy for them to repeat that pattern over and over and over. This may be the spot they want to focus on. This run right here seems to be nice and level, nice and flat. And if they can continue just pushing it into the scoring zone and keeping it nice and level and flat the entire time, I think they'll be happy with the material that they collect. There is a wall of material that just will not fall out of their dozer blade. But this team has chosen to keep their robot small, lightweight, and as simple as possible. So they chose not to create, to add any sort of like vibration motor to their system like we've seen other teams do. And hopefully they can, maybe towards the end of the run, maybe they can shake their robot in a way that will release that material from their dozer blade. They're roughly halfway through their run, and they are just now getting a good amount of material in the scoring zone after having a little bit of problems with the first spot that they chose to dig in. Oh, this looks promising. They're going to have to lift up a little bit. They're starting to slip a little bit, so they're pushing maybe a little bit more than the robot can handle. Maybe I was wrong. Maybe the robot can handle it. That was a lot right there. That was a good load. Most of it is in the scoring zone. They got to be happy with that run right there. With 14 minutes remaining, let's see if they can keep this momentum. Now, if they did dig a low spot in front of the robot is going to dip down into that low spot. And if they don't compensate by raising the bucket, that could cause them to stall. So we'll see how the students handle a repeat on this same track. Yeah, they did raise the bucket a little bit. You could see they lost some of the material that they were pushing, but in the long run, that might be exactly what they want to do in order to keep this little runway that they've made relatively flat. All right, hope the students are keeping an eye on that rock, because I don't think the robot wants to try to drive over that rock. All right, looks like they're going back to the first spot that they had tried earlier. That's good. As the robot was starting to tilt upward on that last cycle, you could see that they were trying to lower the blade to compensate. So they were compensating a little bit. We'll see if it was enough to allow them to run over that path again and have an easier time with it. 11 minutes left in College of DuPage's first run in Lunabotics Finals 2025. This robot does have some sensors on it that could be used for automation. The students are not running autonomously right now. They may run this entire run without autonomy and maybe try it again on their second run. The black puck-shaped cylinder that is centered high on the robot is very likely a LiDAR, a laser scanning device that can give you a 3D representation of what it sees all around the robot. Those are commonly used to create a 3D representation of the surface that surrounds your robot. Got a really good bite there. Can they hold on to it though? Because now the robot's going uphill, or it's about to go uphill. So can they hold on to this material? If they lose too much, they're actually compounding the hill right there. That's what makes this so hard. Once you have a little bit of a uneven surface with a dozer, you can actually fairly easily, without even trying, you can pretty easily make it worse. It's easy to make it worse. It's hard to fix it. Another sensor that I can see in front of the black puck is a black rectangle kind of shape, which is very likely a depth camera that also gives both 2D views of what is in front of the robot, but also 3D views of what is in front of the camera, and possibly showing what is in the blade, in the dozer blade. Yeah, that dozer blade just went over the hill that they just created, so that wasn't very productive that particular time. But these students are persistent. They're going to keep trying to work in this area and try and level out this spot, because there's a potential for a lot of material here that they could potentially push into the scoring zone. So right now the dozer is pointing a little bit downhill, and now it's going to go uphill. There's the problem area. So they're trying to compensate by pushing the blade down. There you go. That's going to help right there. That'll help a little bit. If they can do that a few more times, they might be able to smooth out this problem area. And I may be blowing it out of proportion. The students may not consider this a problem area at all. This may be exactly what they're trying to do. 7.5 minutes in this run for College of DuPage. Their first run of 2. It's amazing how much material is sticking in the front of that dozer blade and is just refusing to fall out. I want to point out that this material is dry. There is little to no moisture in this material. The reason it is sticking is because the particles are jagged and super small, like talcum powder small. And the jaggedness of these particles, the roughness, is making them lock together like puzzle pieces. And this is part of the reason we put on this event, is to help us try out different prototypes of how to deal with this really unique material. And NASA can come away from this event every year with a lot of different ideas and a lot of different prototypes, and be able to see what works well, what doesn't work so well, but might have promise for future development. Okay, this is a good bite right here. except they lost it right. They lost most of it right there. So if they back up and try again, they might be able to recover. Yeah, they're working on it. These students are working on the problem piece by piece. They've got a little bit of a down and up and back down situation in that path that they've created. If we go to camera 1 for a second, the side view, we'll be able to see this pile of material that they have deposited into the scoring zone is nothing to sneeze at. This is a good amount of material, especially compared to the size of this robot. So by the time the judges compensate for the weight of the robot and the power used by the robot, it could be, really competitive final score. There we see the students in mission control do not appear to be frustrated. We've got smiles and positive attitudes. So I think these students are happy with the amount of material that the robot is able to get into the scoring zone. And just in the last 5 minutes, they've made a lot of progress. 4 minutes remaining in this run for DuPage. They're slowly inching the scoring material forward inch by inch, kind of scooping off the high spot. Every run, it appears that they're scooping off the high spot of this track that they've made. I hope everybody cheers later when all the material stuck in this dozer blade falls out, especially if it falls out into the scoring zone. That's going to be amazing. We're under 3 minutes for DuPage's first run. Two minutes left in this run, and they've been making amazing progress just over the last 10 minutes. These students have really found their groove in the last half of their 30-minute run for sure. Okay, we're under a minute in this run. Are they going to get some more material pushed in the last 50 seconds? Hopefully. See, the blade lifts up right there every single time. They are knocking out that hill right there, slowly but surely. 30 seconds left.
Attention in the pits. If you're staying in Town Place Suites, we found your hotel card.
All right. As time winds down for College of DuPage, look at that mound of material that they have in the scoring zone. Let's give College of DuPage a big round of applause for a job well done on their first run. Look forward to seeing what they do in their second run tomorrow afternoon. So looking ahead on the schedule, College of DuPage was our 10th team to get a first run, and now we are going to go back to the top of the team list, and Michigan Tech is going to run next, and we are now starting the second runs for all 10 teams. This is a milestone. We are halfway through this competition. Every team has now had one official scoring run, and we're about to run through them all again for the rest of today and tomorrow. We'll give all 10 teams a chance to do their second run, and it's the final score for each team is going to be the summation of the scores from their first and second runs. So coming up next is going to be Michigan Tech performing their second run, then University of Virginia, then University of Alabama, and then Milwaukee School of Engineering. By the time we get through Milwaukee School of Engineering, it'll probably be 6 o'clock p.m.-ish, and we will probably call it a day. And then that'll leave 6 teams for us to run tomorrow for their second runs. So as we watch the College of DuPage team clean up the robot and pull it out of the Artemis Arena, and as we watch all 10 teams working hard and relaxing in their pits, don't go anywhere, because Michigan Tech is coming up next in just a little bit. You're watching NASA's Lunabotics 2025 Finals event, streaming live today and tomorrow, yesterday, today, and tomorrow from NASA's Kennedy Space Center Visitor Complex here in Central Florida. Don't go anywhere. We are watching the Michigan Tech students in mission control putting the final touches of the setup of their system. Their robot is currently in the arena in the starting position. The students are still there for the next few minutes, putting the final touches, making sure everything is working on the robot before they leave the arena. What we're about to see is the Michigan Tech team perform their second of 2 runs this week in NASA's 2025 Lunabotics Finals event. This Michigan Tech robot does have some autonomy features. It does have some 3D depth sensing cameras on it and software that can recognize and avoid obstacles and things like that. We see this Michigan Tech students leaving the arena, an indication that they are happy with the robot's power on and self-test, and that they're ready to start their run. In this view, you can see the rear of the robot. Well, I'm going to call it the rear of the robot, which is the dump side, versus the front of the robot, which I'm considering the dig side. Yes, that does gel with the arrow I see on the robot. So the rear of the robot, where it says student driver, there's a camera there looking downward in order to see probably the Regulus simulant exiting the robot, possibly also recognizing whether the robot is in the correct position for dumping. There's a similar camera. If you see the red button in the upper right of the screen, there's a camera directly to the left of that red button that is forward looking, and I'm guessing is there to recognize obstacles for the robot to avoid. As soon as the Michigan Tech students have left the arena, and as soon as our arena judges and mission control judges are ready, we will start a 30-minute run for Michigan Tech, their second of 2 in this year's competition. As we saw the first time this team ran their robot in the arena, the wheels of this robot, all 4 of the wheels are steerable. So not only are they all 4, is it a 4-wheel drive robot, it's also a 4-wheel steer robot, which can give the robots more maneuverability than a robot that is not 4-wheel steer. Can also spin in place without dragging wheels. I just realized the rear wheels can steer a little bit tighter than the front wheels. This robot is not symmetrical to the point where all the 4 wheels can steer the same amount. That's interesting. Didn't appear to affect this robot's ability to spin around, as we just saw. All right, so the robot presumably just mapped the obstacle zone and apparently has driven into the wall. Now, the students have not grabbed the joystick, so this robot, even though it appeared to go too far, the students remained cool, calm, and collective and are letting it run because they will get extra points for autonomy. Yeah, the students had to take over manual control there. I believe the judge might have even stepped in there. Not sure. But they're obviously past the obstacle zone and are now lowering their digging implement, their bucket ladder system. So the student in the middle is controlling a joystick right now. From what I can tell. And this thing goes pretty deep, so it's powerful enough to go beyond the first couple inches of light fluffy stuff and push into the really tough stuff. And you can see this is a great view of their onboard conveyor belt where all the material is deposited. Now they just got to drive over to the construction zone in order to put this place this material into the scoring position. The front, oh my gosh. This robot says, "We love you, Kurt," on the back. I love that. I love you too, Michigan Tech. So this team, I'm fairly certain they're driving this robot manually. Just really hard to tell. I think there's a student holding the joystick right now and driving this robot manually, which makes sense. It would be a really crazy feat for an autonomous robot to drive into a hole like that and be able to get itself out. In order to deposit material, this robot is going to have to basically spin around 180 and basically dump out the backside. I want to point out that I am not a judge, so you can suck up to me all you want by putting "We love you, Kurt" on your robot, but it's not going to get you any more points. All right, this is a good first deposit from this team. Which I believe this run was done manually. Yeah, I can still see the joystick in the students' lab. Okay, excuse me. The students just this second put their joysticks down on the table, so I think they're about to activate an autonomous dig and dump cycle here. Yep, the students are hands off. The robot is moving. It has put its excavation, its bucket drum system, over into the excavation side.
70-30, starting in 5 minutes. Please make your way to 70-30 if you're interested in the Caterpillar seminar. Thank you.
You can see the conveyor belt spin slowly while they're excavating in order to spread out the onboard material. The bucket ladder arm is rotating down in order to push down into the deep below the surface, and now they're backing up. All autonomous right now, and unloading. So if you just think about that cycle we just saw, that only took about 1.5 minutes. So things are about to get highly productive here, I think, and autonomous. So it basically is starting where it left off, it looks like. Spinning up, pushing, rotating that bucket ladder system down below the surface until it's almost straight up and down. And that is basically full depth when it reaches its endpoint. Oh, it hit really hit some hard stuff there. Did you see how much it jerked right there? Didn't seem to break anything, didn't even seem to bind up their system. So they have enough power in their system to handle that kind of tough resistance. Handling that kind of tough resistance is important, but you have to remember all of these teams are also trying to make their robots as lightweight as they can, and also as power efficient as they can. And so these are some of the trade-offs. If you make it too lightweight, it's just not going to be tough enough to handle being beaten up like that. And if you make it use too little power, if you go too far, then your motors are going to stall, bind up, and not be able to power through the really tough stuff. So just another example of the trade-offs that all of these teams, not just the 10 that are here in the finals, but all 35 teams that competed all year long to design and build and test these robots. You see how deep that trench is that this robot is leaving behind. The near part of the trench, the part of the trench that's towards the right in this image, doesn't look as deep, but that's because it's kind of filled in from material dropping into it. Oh, the robot just turned its wheels, and now it is picking a track that is not the exact same spot that they were on earlier. So it has shifted to the right by 6 inches or so. I'm looking at the students to see if they've taken over control. I think the student may be holding the joystick right now because it was on the table earlier. Yeah, I think the students may have decided to hop back into manual mode in order to maybe maximize their throughput. This is a trade-off too. I mean, when you create autonomous software, a lot of times it gets the job done, but it's maybe not as aggressive as a human driver. And so now if this team has decided they've got enough autonomy points they're happy with, that they can be really aggressive manually and just try and maximize the amount of material that they bring back into scoring position. Now, this robot is in a precarious position right now because one of the wheels is dangling in midair above that trench that they had just autonomously dug. So only 3 of the wheels are reacting to these digging forces right now. The rear left wheel is basically hanging in midair over this trench. Now that they're digging manually, you'll notice that they're going to continue to dig until that conveyor belt is completely full, even possibly overflowing. You're seeing they're driving forward while they're digging, and they're really pushing. You can see how the material is piling up on that conveyor belt on board the robot. They're pushing this robot pretty hard in order to maximize. Now, this is an area of the digging zone where the front right wheel is now over, it's now falling into a crater. And so right now, I'm not sure how many wheels are touching, but the answer is definitely not 4. There's either 2 or 3 wheels touching the ground right now. Looking at body language in the control room where these students are controlling this robot manually from a joystick, they are definitely focused on the computer monitor that we have provided. So they've chosen to use one of the arena cameras that we're providing, and to take a point hit, a little bit of a penalty for using that camera. But using that camera probably gave them the visibility into where how precarious they were situated just then over that trench and over the crater in that area. So I think probably using that facility provided camera really probably was the right choice in that scenario. This is going to be a really good angle to show how aggressively these students are going to push this robot right here. And even though they're not running autonomously right now, they're probably happy with the autonomy points they were able to get earlier. And now they're going to just see how much they can push this robot, hopefully without breaking it, and see how much material they can get deposited, excavated, and then deposited into the scoring position. And so much time remaining, 16 minutes remaining in this run for this Michigan Tech team. I will say that there is some dust you can see on this camera view. Judges are making note of that, so there's a little bit of a penalty being applied because of the dust that's being lofted by this robot during their run. Okay, they're running backwards. Usually when you see a digging implement running backwards, it's had a problem. Maybe it collected a rock that bound up its, oh, there it is carrying a rock right there. But when you've got a chain system or a conveyor system, sometimes rocks can bind up your system. But if you run them backwards, usually you can throw that rock back out the way that it came in. Fourteen and a half minutes remaining in Michigan Tech's second of 2 runs. A lot of time. They already have a respectable amount of material in the scoring position, and there's still a lot of time to add a lot more material to that pile. Getting a nice close look at their at the Michigan Tech digging arm, their rotating bucket ladder system. The buckets are basically attached to a chain. You can see it slowing down right there. They hit a pretty tough spot. Looks like they got past it. Oh. For a second it looked like one of the buckets was facing in a direction that it shouldn't have been, but I think it corrected itself. They're really getting a lot on board this time. It bound up just then, but they're backing off and starting it up again. All right, they're saying that's enough. We got a full load. That's a lot. There's a lot of material. And so much time left. 12 minutes left for Michigan Tech. This is their second of 2 runs, so it makes sense for them to be aggressive with their digging, to drive it like they stole it, as they say. This is a fun angle. We can actually see the dirt falling onto the conveyor. I get bound up right there. I noticed each bucket has some writing on it, possibly a little message from each student, maybe even their autograph. That's fun. Okay, they didn't dig a whole lot right there. Are they going to pick a different spot? Yeah, I think they're going to pick a different spot. You can see how much the robot is shaking, being shaken by this operation. This material is really resisting these digging forces when you get down below a few inches, and so they're I don't know, probably 12 inches down, so they're in the really tough stuff. So once they've fully rotated their bucket ladder down to as deep as it'll go, they have a choice of driving the robot slowly, either forwards or backwards. And they're going forwards right there, you can see. This team has covered their robot with "We Heart You Kurt" stickers. There's more than one. I love it. All right, I think that is probably considered a full load. You can see the trench that they have just dug. Very, very good sized hole right there. A deep hole that they could come back and make longer if they choose. the side view shows is a better angle showing you the size of these piles. So very respectable sized piles. I think they've decided the first pile was big enough, and now they're going to focus on this second pile, I think, for the rest of the run, with under 8 minutes remaining for Michigan Tech. In my research the other day, I found out that Michigan Technological University actually started as the Michigan Mining School in 1885. Michigan Mining School, which is kind of cool. Mining used to be the thing, and it's basically, mining has basically turned into engineering. Look at the rock in that, in camera 3. It's a pretty good sized rock. I think it might be stuck in that. Six minutes left for Michigan Tech's second and final run of this event. Part of this 30-minute run for Michigan Tech ooh, there's a big hole right there. Wow. I'm not sure the team saw that. That robot really went diagonal there. Now the rear wheel fell into one of the holes that they had just dug. So you've got the front wheel in a pretty decent hole, and you've got the rear wheel in a different hole. That's one of the trade-offs for all of these teams. They know when the rules come out, they know the size of this arena is limited. Looks like they're heading back towards the obstacle zone. Maybe they want to get some obstacle points for autonomy. This is not the first team we've seen do this late in their run. They have 4.5 minutes remaining, and they appear to be going back to the starting zone, the starting position. You can kind of see their tracks from earlier. Going back to the starting position, and if we see these students put the robot into an autonomous drive across the obstacle zone, and then go hands off. The joystick is already on the table, so they're hands off the joystick. If we see this robot drive across the obstacle zone in the next 4 minutes with the students completely hands off, they will have earned some really great autonomy points. But the students decided that they really needed to get a lot of material manually put into the scoring position before trying this. Something didn't appear, I could be wrong, but it seemed like they did try this at the beginning of their run and didn't seem to work, and so they gave up on the autonomy attempt and started driving the robot manually. But now The students feel like they're in a pretty good position, and it appears that they're going to try for this autonomous drive across the obstacle field one more time before time runs out. They are under 3 minutes, though, so time is running short. The robot is not moving yet. Both the joysticks are on the table. Students appear to be patiently waiting for the robot to do its thing. Okay, the robot is moving. Okay, this is exciting because time is very short. 2 minutes and 10 seconds to autonomously drive across the obstacle field. Okay, that's kind of what it did the first time. Now it's turning. That's kind of almost exactly what it did the first time. So with 1.5 minutes remaining, it appears the students have grabbed the joystick and backed the robot up. So that second autonomy attempt to drive across the obstacle field appears to have given the same results again for this team from Michigan Tech. 1 minute remaining in their run. I'm not sure what they'll be able to do with this minute that remains. I think the students are just relaxing and appreciating and enjoying the run that they just had. So as time runs out on Michigan Tech, let's put on camera 1 to show off the pile of material that Michigan Tech has delivered into the scoring zone. Let's give Michigan Tech a big round of applause. This was their second and final run for Lunabotics 2025. Great job, Michigan Tech. Regardless of the outcome, I hope your students are satisfied, happy. I'm seeing high fives and smiles in the control room. So the students are happy with their performance, and that is great to see, regardless of where they end up in the final standings. So that was Michigan Tech's second run. Up next, we're going to have University of Virginia perform their second run. After that, Alabama, and then Milwaukee School of Engineering. That's what's coming up next, so don't go anywhere. You're watching NASA's Lunabotics 2025 Finals event, streaming live from NASA's Kennedy Space Center Visitor Complex. Don't go anywhere. We will be back soon with University of Virginia.
Did you know there's been over 1 million registrations in NASA's virtual guest program since May 2020? From your neighbor to the Crew 5 astronauts, you might be surprised who is a NASA virtual guest.
Do you have Mars 2020?
I do. Do you have James Webb?
Sure do. Do you have Crew 5?
Well, I've got it here, and you guys have it here, but I missed it here.
We conducted over 200 science experiments and technology demonstrations on our mission. We loved being part of Expedition 68. We even remembered a virtual guest passport for Einstein, our freefall indicator, but we forgot to register and missed the stamp.
Even if you're doing existing research, never miss a stamp from NASA's virtual guest program. Whether you're en route to the International Space Station or located anywhere around the globe, register at nasa.gov/virtual guests to receive updates on missions and milestones. As a virtual guest, You will receive curated resources and a stamp for your passport following a successful launch.
Remember, you only get the updates and stamp if you register.
I joined. I won't miss it next time.
We are now watching the University of Virginia team during their 10-minute setup period. Students in the arena have powered on the robot, and the students in the mission control are powering up their computers and networking equipment and making sure that they can send commands to the robot and receive data from the robot. It looks like he's talking to a banana. College students, am I right? Obviously, students competing here this week have not lost their sense of humor. As serious as a competition like this can sometimes be, it's great to see students having fun and still competing well and succeeding in this highly technical robotic mining competition. And their run has started for University of Virginia. Virginia student appears to be driving this robot through the obstacle field with their joystick and communicating with each other still in the control room using bananas. This Virginia robot is almost into the excavation zone where they are allowed to start digging. You'll remember that this Virginia robot has a large center-mounted bucket drum that actually plunges downward to dig deeper. Each pass of this bucket drum is only digging an inch or so, but if they plunge it downward, it goes deeper. And now they are digging only 2.5 minutes into their final run. You see the robot obviously drives while it's digging. Looks like they bound up on something there for a second. During their first run, this team really deposited a lot of scoring material into the scoring zone. Looking at just the amount of material, the volume that was placed into the scoring zone, Virginia was in the top 3 during their first run. That being said, the final score takes into account a lot more than just the amount of material deposited into the scoring zone. Autonomy being a very large part of the final score. And this Virginia team, even though the robot does appear to have some sensors, like possibly even a depth camera up high on the end of a 3D printed blue colored boom, it's possibly a depth camera. This team does not right now appear to be running this robot autonomously. They appear to be stick driving. And there, the side view of the robot, you can see right through the drum. It has clear plexiglass sides on the drum, which is pretty great for seeing how much material has been excavated and picked up by the robot. This robot's going to get heavier and heavier as more material gets pulled inside that drum, which could make it harder and harder to drive as it gets heavier and heavier. You can see if they try and push too hard, their digging system binds up. So if they try and dig too aggressively, the robot says, sorry, can't do it. So the students are going to have to push just hard enough to push this robot right to the edge, but not any further. If they want to maximize their, oh, there's a hole right there. A little bit of a crater in the obstacle zone that the robot left side just fell into. The excavation zone is not free of obstacles, obviously. You can see 3 rocks in this view, plus the craters. There are a couple of them, as far as I can see. Virginia team appears to be making sure they get the robot on the far end of the deposition zone or the scoring zone, so they have plenty of time and plenty of space to deposit all the material that they plan to deposit during this 30-minute run, their second of 2 runs during this year's competition. So the rotating bucket drum is a fairly simple design. No moving parts in the drum itself. You just rotate the entire drum in one direction to dig, and you rotate the entire drum in the other direction to offload or dump. Looks like they're going to that same spot that they had just come from in order to dig possibly another level down, another level deeper, possibly in that same spot. I just realized they drew teeth and a tongue on their bucket drum. Okay, they're going to maybe start here and go off in a different direction. Yep, they're going to start here and then head off kind of diagonally. basically digging a shallow trench in a slightly different direction. There is a crater over here in the corner, I believe, that this robot might fall into at some point. Maybe not. Oh, there it is. Front left wheel just kind of sort of fell into a hole. At least I think. I don't know, that might be the back. I don't know which way is front on this robot. Okay, I did have it backwards. I can see the arrow now on another screen. The front of the robot is facing the camera right now. Haven't seen movement in a minute. We can see the bucket going up and down just very slightly. Students may be troubleshooting maybe some communication problems. The students in the control room are staring intently at one of the monitors, one of the cameras that we are providing for them, and we are giving them control over. I noticed they have not zoomed in to anything in particular on their robot. Sometimes when a team zooms into a certain part on the robot, it kind of helps us understand what's going on, what they're troubleshooting. We didn't have a good camera angle. I wonder if the wheel that was over the crater, I wonder if that one wheel was just free spinning and causing the other wheels to just not move at all. Not sure what happened just then, but there definitely was a pretty significant crater in that corner of the arena that may have caused some issues or concerns for this team. But we seem to be back on track. 18 minutes remaining. Plenty of time for this University of Virginia team and their robot to excavate, transport, and deposit a lot of material into the scoring zone. Their drum that time wasn't quite as full as we've seen it before. We have in the past seen this drum from the little side window. We have seen this drum roughly half full before. All right, here we go for another cycle of digging, transporting, and depositing. still in manual control as far as it appears from looking at the students in the control room. Appear to be stick driving this robot so far throughout this entire run. Although only the judges in the mission control room know for sure. Okay, they're digging pretty aggressively right here. They're going pretty deep, and the robot's driving pretty fast. You can see the digging drum bound up there for a second, and the wheels started slipping. That's what happens when you push it too hard. And now they're back to digging. There's a crater on the left, which is causing the robot to tip. This robot has a pretty low center of gravity, obviously, though, even though it has some things. It has some things up high. All of those things that are up high are very light and minimal. All the electronics on this robot, which we're about to see, are very low. Obviously, the wheels and motors are all very low. The digging drum is as low as it can be. And so this robot not really concerned about tipping over even when driving into a pretty good sized crater. All right, taking another pass at this spot. Moved slightly to the right, I believe, from the former pass, the prior pass. Okay, they're shifting. Either shifting to a different dig spot or shifting to prepare for a deposit. Okay, they're going to dig right here, driving towards the camera now. So we're seeing a reverse angle than we saw before. Get to see all of these wheels if they react. If any of these wheels lift up in the air, then they've maybe pushed the bucket too far. As long as all the wheels stay in good contact with the ground and are providing good traction, then they are digging at the right, an appropriate level. Oh, we have having some slippage there. They pushed it a little too far. There is a rock there. I don't know if the students can see that. Yeah, I think they can see that. They are definitely watching an overhead camera, similar to the one that we are watching. Oh, actually, you were actually watching the same camera that the students were. I had my eyes on a different camera at that moment. All right, we'll look at the side view of the digging drum now as they pull into the scoring zone. See how full their bucket drum is right now. We have seen them put more than that in, but that is a significant amount of material. That is a lot of good scoring material right there. 12 minutes remain in Virginia's second and final run for this year's Lunabotics event here at NASA Kennedy Space Center. And so much time left for Virginia. They got 12 minutes left. Let's see where they go this time for this dig pass. They're going to go to the left of that rock. Nope, they're kind of going back to that spot they just came from. Looks like they're going to dig in that exact same path that they just were in, more or less. And basically go a little bit deeper into that same spot. All right, they made one pass, 10.5 minutes remaining. Are they going to do another pass or deposit this material that they've got on board? Doesn't look like, it's hard to tell that they got a bunch on board based on their clear window on the side. It's possible they weren't pushing down hard enough on that last pass to really make a dent. I don't think, I'm looking at the trail left behind. I don't think they're doing very much digging right now for some reason. Because there should be a nice trench left behind between these wheel treads, and I'm not seeing a nice trench pattern in the soil. They do have some on board, though. It's a little bit less than they had before, or about the same. I suppose if this robot's leaning to the left or right, it's going to be hard to see through the plexiglass how much is in there, because you'll get a false reading if the robot is not level. That may have been what happened there. Threw me off. Eight minutes left. 8 minutes left for University of Virginia's second run. Looks like they're going, I was going to say back to the same spot, but they've just changed direction. They're going to pick a new spot, maybe. Oh, or they're just turning around. That's probably more likely. Nope, they're going to dig right there. You know they're digging when the robot jumps and jerks like that. And you know they're digging pretty aggressively when it binds up like that. So this is a pretty aggressive path right here. for University of Virginia. And they're not done yet. They're going to dig some more. I thought they were going to deposit, but I was wrong. I do want to mention that we've seen a lot of robots that have an obvious front and an obvious back. And in order to minimize the robot having to turn around in the middle of their dig dump cycle, you know, they position the robot facing a certain direction. But I will say that this robot design really doesn't have a preferred direction for digging or for dumping, honestly. Matter of fact, they've been digging sideways, 90 degrees from the path that this robot needs to drive in order to deposit into the scoring zone. But if for some reason this robot got turned around, I think they could still do the digging and they could still do the dumping from the other direction with very little impact to their efficiency, their overall system efficiency, I believe. So the more puffs of simulated regolith that come out of this digging drum as it spins is probably an indication of how full, even though it looks about half full, it's likely that it really can't really hold much more than what's in the drum right now, even though from the side it looks to be only half full. Because if you were to try and fill it up much more than it is right now, I think every time the digger comes around, you're gonna lose almost as much material as you gain inside that drum. And so this team likely knows that based on all of their experience and testing, and so they probably know that if they fill this drum halfway or more, it's probably not going to do them any good if they try to fill this drum halfway or more. I mean, 3 minutes left for University of Virginia. And if we look at the side view, we'll be able to see the piles of regolith simulant from a better angle. So from this view, you can see 3 piles, pretty good piles. And remember the first run for this team, the amount of, the size of the berm that they created in their first run was in the top 3 if we were just focused on berm size. And they appear to have done a good job again on their second run. However, without autonomy points, we will see if it is enough to win this competition overall when you take all of the other considerations into account. I would venture to say, regardless of the outcome, all of the students that compete in this event have a good time and have a positive experience and learn so much by going through the entire school year's worth of being a member or a leader on their robotics teams that compete in these NASA Lunabotics events. These teams learn about the NASA systems design process. They learn about mechanical engineering, electrical engineering. They learn about software engineering. They learn about engineering design trade-offs. Invaluable experience. Just putting a competition like this on your resume just is an amazing way to give yourself an edge over applicants that just don't have this sort of experience. It's just immeasurable experience. 30 seconds. Virginia has just enough time to offload their final trip. And then look back at the side view from camera one and enjoy the 3 piles that they have deposited into scoring. So as the timer runs out on University of Virginia's second run, let's give University of Virginia a big hand for a job well done here in this competition this year. Great job, Virginia. Now, next on the schedule is going to be University of Alabama. And then after Alabama, we will have Milwaukee School of Engineering. So don't go anywhere. You are watching NASA's Lunabotics 2025 finals event, streaming live from NASA's Kennedy Space Center Visitor Complex in sunny Central Florida. Don't go anywhere. You do not want to miss University of Alabama's run coming up soon.
I'm Christina Cook. I'm a mission specialist.
I'm Jeremy Hansen. I'm a mission specialist.
I'm Victor Glover. I'm the pilot.
I'm Reed Wiseman. I'm the commander for the Artemis II mission to the moon.
To the moon.
To the moon.
To the moon.
When I was young, I had a poster of the Earthrise picture, the famous picture that was taken on Apollo 8. And the fact that it was a human behind the lens that made that picture so profound and changed how we all thought of our own home was so amazing to me. The moon is not just a symbol of thinking about our place in the universe. It's not just a symbol of exploration. It's actually a beacon for science. It's a beacon for understanding where we came from.
You know, pushing ourselves to explore is just core to who we are. It's a part of being a human. That's our nature. We go out there and we explore to learn about where we are, why we are, understanding the big questions about our place in the universe. The exploration we're doing is the first few steps on the path of getting humans to Mars.
The Artemis campaign of missions have set such an ambitious goal for humanity that it's inspiring contributions from around the globe. Not just one nation is inspired and moved by this, but nations from around the globe are coming together. When I look at the Artemis II crew with Victor, Christina, and Jeremy, they want to go do this mission. They are keenly driven. They are humble to a fault. It is so cool to be around them. Artemis II is a huge mission, but I hope we will look back and realize that this was one tiny step in humans on Mars and a sustained presence on our moon.
Before stage engine start.
Artemis II will be NASA's first crewed flight test of the Space Launch System rocket
and Orion spacecraft around the moon.
To verify today's capabilities for humans to explore deep space
and pave the way for NASA's long-term human and scientific presence on the lunar surface.
We are ready.
We are going
to the moon
for all humanity.
We are Artemis.
It's a new day in space exploration. As we sail on this new cosmic sea, there's so much to learn. There's so much to be excited about.
Artemis is different from anything humanity has ever embarked on before. And we will discover life-saving, earth-changing science and technology along the way.
We're delving deep into what science can be achieved by humans working together with robotic capabilities and future infrastructure to support a long-term human presence at the moon.
The Artemis generation stands ready to return humanity to the moon and then to take us further than ever before to Mars.
We are watching the University of Alabama team prepare for their second and final run in NASA Lunabotics 2025 finals event. The students who placed the robot in the arena are now appear to be exiting, and the students who are controlling the robot in our mission control room appear to be ready to go. So as soon as our judging staff goes through their checklists and make sure that everything is in the proper state that it needs to be to start this run, they will call the start of this run. There's a good close-up view of the bucket ladder digging system, and there's a good view of a visual target that this team has installed in the corner of our starting area for the robot to use to keep track of where it started. And to use throughout the mission to calculate its current location and orientation or rotation. This Alabama team has a history of running most, if not all, of their runs autonomously, which can give them a huge scoring advantage over teams that do not run fully autonomously. We will be trying to watch the students in the mission control room using our camera to see if they're giving any body language indicating whether they're fully autonomous. But only the judges in the mission control room know for sure whether these teams are running fully autonomously. The Alabama team has just turned off the 2 monitors in the control room that provide optional cameras. So the team is choosing not to use the 2 optional cameras that they're allowed. They don't need them. They've got enough sensors on their robot and cameras that there's no reason for this team to use any facility cameras or cameras that imitate cameras that might be on board a lander that had just dropped this robot off on the moon. These are the Alabama students in the control room. Waiting for their 30-minute run, second of 2 runs, to start. All the students appear to be sitting far enough away from, and we have begun. They hit one button to apparently start the robot, and students are nowhere near their computers and do not appear to be holding any joysticks. The robot is turning in place. This is a 4-wheel drive skid steer robot. The robot obviously is looking at the visual system that's been put in place for it to use to calculate location and orientation. And now I suspect it's going to do a spin, continue that spin in order to map Well, honestly, if it's using its LiDAR, its laser puck, which is centered on top of the robot, if it's using the laser puck to map, it doesn't really need to spin. These puck formatted laser sensors are actually spinning 360 degrees around the robot, which means you don't have to spin the robot yourself in order to create a map of the area. Now it is hitting that rock, so it either didn't see it or it didn't care. It has successfully driven over that rock without the students controlling it directly. Automation software appears to be operating right now. There are different tiers or levels of automation that teams can attain in this event. And getting across the obstacle field fully autonomously is just one tier that a student team can attain. Another tier is a single cycle of digging, transporting, and delivering material. Another tier beyond that is actually 3 cycles of digging, transporting, and delivering. And if memory serves, the only tier better than that is to run your entire 30-minute run fully autonomous. That is the top tier for autonomy. So far this team from Alabama appears to be getting through the first tier of autonomy. The robot did stop, but it's possible that it just stopped so that it could map the area. Even though the students right now are not touching their computers, they do have their eyeballs on their laptop screens, and they are seeing what the robot is telling them. And so if the robot is telling them, I'm okay, I'm doing this task, it is succeeding, then it does behoove the students to let it continue in order to try for those autonomy points. Because those autonomy points, especially the upper tiers, are worth so much, they can really make a huge difference. Okay, the students' body language appear to be about ready to take over manual control in the control room right now. They've got their fingers hovering over their keyboards, but they haven't touched them yet. All right, they just touched the keyboard. And probably manually controlling right now. So something apparently went wrong. So they may have aborted that very first tier of autonomy. They still have several other tiers of autonomy to try for remaining. The next one being one complete cycle of digging, transporting, and delivering material. as a software engineer, it's kind of fun to look over the shoulder of these students as they type on their computers and see what pops up on the screen to try and figure out what exactly they're doing. There's a non-zero chance they're restarting something on their robot software-wise. Maybe some process locked up and they killed it and restarted it. Okay, robot's moving again. Ooh, there's a rock right there. But this robot has enough ground clearance to get past it. All right, what I suspect the students are going to do is line this robot up in order to kick off an autonomous dig, transport, deliver cycle. So they're backing the robot up into its future delivery spot. And they're probably kicking off some automation software right now in the control room to tell it to autonomously perform that dig, drive, deliver cycle. This is taking a bit of time. It's starting to get a little bit concerning because we have 21 and a half minutes left. So 8.5 minutes into a 30-minute run, and this Alabama team has not brought any material to the scoring zone yet. Once they get this robot going, it could go like gangbusters though and make up for this time. All right, we see movement in the direction of the excavation zone. There goes the spinning bucket ladder system. It's spinning fast, rotating down. There, it's just made contact, and you'll see some reactions from the robot as it hits the tougher material, driving forward slowly. So right now it is digging and dumping this material into its onboard conveyor belt. This current path is going to come kind of close to that rock, but probably will miss it. The students probably had a pretty good visual on that rock and knew that this was a good path to take. There are so many cameras on this robot. Several two-dimensional visual cameras and several what appear to be three-dimensional depth cameras. In addition to that black and white cylinder centered on the back of the robot, which is very likely a LiDAR system or a laser scanner. The laser scanner will give a very high resolution, highly detailed surface map of the area around the robot. Oh, I should mention the students are hands-off, so they definitely have started this cycle in autonomous mode. So that dig that we just saw and this transport that we're seeing right now and the deposit that we're about to see, completely autonomous. So that is going to give them one tier of autonomy points. And if they remain hands off and it does this 2 more times, I believe, they will jump to the next tier of autonomy points for being able to do this 3 times completely hands off. So let's see if it does it again. 18 minutes remaining. There's a reasonable likelihood that if this robot fails to do this 3 times autonomously or succeeds, regardless of whether it fails or succeeds in doing this 3 times, there's a reasonable likelihood that the students are going to be happy with their autonomy points, realize that they won't get any more autonomy points than that in this 30-minute run, and so highly likely that they will take over manual control and do some really aggressive manual digging at that point for the rest of their time. You can kind of see in this image on the upper left of the robot the trench that was dug just prior, and you can kind of see how deep it is. Several inches, it looks like. Sometimes it's hard. Sometimes you lose sense of scale when there's not a person in the image. But I believe that first trench was probably around 4 inches deep. I'm just guessing, no, I could be wrong. I've never been wrong before, but this could be the first time. Even in autonomous mode, this robot is being quite productive. If we go back to camera 1 for a second, if we go to the side view and look at the size of that first pile, that is just one cycle. That is just one dig pass that you're seeing in the scoring zone there. So that is not an insignificant sized pile. So even under autonomous control, this robot is doing a fairly aggressive amount of work. So imagine after doing this 3 times and getting the autonomy points they want, and then going really aggressively, imagine how big the piles are going to be that they unload into the scoring zone. All right, so for its 3rd autonomous pass, is it going to shift to the right? It looks like that second pass shifted to the right a couple inches. You can see the original tracks and then the second pass tracks. Are the 3rd pass tracks going to shift again to the right? Was that on purpose? It is. It is shifting to the right. Question is that on purpose, or is it just because that's how the robot just maybe doesn't drive perfectly straight? That's got to be on purpose, though, right? The risk is if they shift too much, then their left wheels could end up falling into the trench that they created earlier. They definitely ended up dumping in the same spot. You can see how the tracks converged back there at the dump site. So My professional opinion is that this kind of sort of fanish shaped dig pattern is on purpose. They've actually coded that to do that. I am just guessing though. 13.5 minutes remain. So we've used up more than half of our time, this Alabama team. But man, in the last 4 or 5 minutes, they have gotten a lot of work done and created a really nice sized berm or hill there in the scoring zone. So their left front wheel is definitely heading directly into their first trench, but it doesn't seem to be a problem for this robot. This camera view shows the front left wheel and the original trench directly in front of that left front wheel. So that left front wheel is either starting to fall in or has already fallen in that first trench. Did not seem to cause a problem for this robot. Probably because these automated trenches are not super deep. That's probably why that didn't cause a problem. All right. So this was the third trip of a dig, transport, deliver cycle. So I wonder if the students are going to continue this automation. Yep, they're letting it go. Is it possible that this automated dig system is more productive than a human driving the robot manually? That would be an amazing feat if this team has created an automated system that is actually better than the human. It appeared to bind up there. Students now are hands on keyboards. Maybe they waited until it started digging to be sure that they had gone through 3 complete cycles. Of course, it's the judges in the mission control that are telling these students whether or not they've hit a tier of autonomy. So now the students are driving this robot manually, and now we're going to see how aggressive these students decide to get with the digging on this robot. This is a tough robot. It can take some abuse. Okay, they're starting their digger just inside the excavation zone, and then I suppose they're going to drive away. They're going to drive to the left, I presume, away from the scoring zone while they're digging. All right, they're digging pretty aggressively. It's binding up their system a little bit, but they've gotten past that. You can see it slowing down. They're driving forward. It's slowing down, but it's not stopping. Slowing down is not a problem. That's probably exactly where they want this robot to operate, I suspect, where it's just got just enough pressure. Not so much pressure that it stops the spinning belt, but just enough pressure to slow it down and give the forces that they need to dig up this regolith simulant. Oh, you know what? They're hands off again. It's hard to tell. This is autonomous, so they just started another autonomous dig and dump cycle. Students are completely hands off of their computers. I don't see any joysticks or game pads in the room. And these students have their game faces on. Very serious. Paying close attention to the data in front of them. Seven minutes remain for University of Alabama's second attempt. Looks like these students are intending to complete the rest of their mission autonomously. And it is pretty aggressive digging, as I said earlier. Kind of tricked me into thinking earlier that it was a human driving, but they've tuned their automation, their autonomy algorithm to get them just on the edge of the forces that it takes to bind the system. Their autonomous software is definitely pushing this robot, but not all the way to the edge. If they really have found the sweet spot where if they pushed it a little bit further it would bind up, then in theory that is better than a human driver. Because could a human driver find that sweet spot and hold it for the entire digging cycle without going too far? Or without backing off and missing out on some material? Okay, those two runs, I'm looking at the wheel tracks, those two passes were over the exact same wheel tracks, which makes me wonder if the earlier three passes were supposed to be over the same three wheel tracks, but something was a little bit off and it made the robot shift a little bit to the right each time. You can see the prior 3 tracks on the left, and then the robot just drove over a second set of tracks perfectly over the first set of tracks. So definitely something slightly different between these two spots. All very successful dig and deliver passes. We're kind of getting into some very minute details here. Since this robot's doing so well, that's kind of got to get nitpicky, right? So you can see those wheel tracks. It's in the same exact spot. I think it's just going deeper each time. So the deeper it goes, the harder material it's going to hit. So it might have a little more trouble. It might bind a little bit more this third pass over that same spot. Still 2 minutes remaining, which means this team will be able to deposit this load and, in theory, still have about a minute left. Not sure what they'll be able to do with that minute. Students are still hands off. So by my recollection, the students manually drove this robot out of the obstacle zone because something happened in the middle of the obstacle zone. They manually drove it out of the obstacle zone into the scoring zone to give the robot a starting place for automated digging and transportation and deposition or delivery. All right, 1 minute left. I guess that's just enough time to deposit this load and celebrate a job well done. So the only part of this 30-minute run that I noticed was manual, was about half of the obstacle zone and getting the robot set up for automated digging. Before that and after that appeared to be autonomous. So a lot of autonomy points probably scored by this Alabama team, in addition to some pretty big piles. We look at the side view camera. That second pile is even bigger than the first. And plenty of time for this robot to empty its onboard conveyor belt. So as the seconds wind down for Alabama, what an incredible run. Even better than their first run from what I can tell. So let's give Alabama a big round of applause for an amazing second run. They got to be pleased with that. So much autonomy. It's just incredible. What a machine. Coming up next, and should be our final run of the day, is going to be Milwaukee School of Engineering. So we will watch the judges repair the arena, and we'll watch students exit and enter the Mission Control Center as teams prepare and judges prepare for Milwaukee School of Engineering to run next. It's going to be their second run of their second and final run of the competition. So don't go anywhere. You are watching NASA's Lunabotics 2025 Finals event, live streaming from NASA's Kennedy Space Center Visitor Complex. Don't go anywhere. Milwaukee School of Engineering coming up next. We are looking at the Milwaukee School of Engineering robot in the Artemis Arena, getting prepared to perform its second of 2 runs in this year's NASA Lunabotics finals. The team did spend their entire 10-minute setup time. It looked like they were troubleshooting something, but I just saw one of the students give a thumbs up in the control room, so maybe everything is now working just in time to start their run. If you were with us yesterday, the Milwaukee School of Engineering robot did end up having some mobility or control issues where the corner, the 4 corner wheels, which are used for steering, got out of sync and were not always pointed in the proper direction, which caused a lot of issues for the team to drive the robot into the spots and locations that they wanted it to be in. Let's hope this team has had an opportunity to correct those problems, and let's hope they have a really productive second and final run of this competition. We are just waiting for our judging staff to verify everything's ready to go and kick off this 30-minute run for Milwaukee School of Engineering. Fun fact about Milwaukee School of Engineering: it's a small school, 3,000 students in this school. Surprisingly, an order of magnitude smaller than our community college team from DuPage. Not even exaggerating, an order of magnitude smaller than the community college of DuPage. But look at this amazing robot that this small team from such a small school has designed, built, tested, competed last week against 34 other teams from around the country, and made it into the top 10 in order to be here competing this week. So their 30-minute run has started, and it would be good to see all 6 of those wheels turning instead of just from this angle. I can only see one. And from this angle, I can only see one. So this robot has 6 wheels. Each of the 6 wheels has its own motor. So it's a 6-wheel drive robot. It's a 4-wheel steer robot, so the 4 wheels on the corners all independently steer. But we are seeing some strange behavior, and the students' body language in the control room is positive. They're smiling, they're even laughing. They do not appear to be panicking. quite possible they are fully aware that this robot is not fully operational right now. And that they are just making the most of the time that they have in the simulated regolith bin. If they end up putting those arms down and digging right there in the starting zone, that would be a major indication that they are not going to be able to do productive scoring with this robot in its current state. This body language is basically saying we give up, but we are still smiling. We are happy that we were in the top 10. We were happy to compete last week. We were happy to have a run yesterday where the robot actually made some good progress and actually did some constructive digging over in the excavation zone yesterday. And so even though this second run apparently did not get the robot out of the starting zone, it looks like this Milwaukee School of Engineering team is giving up. Let's give the Milwaukee School of Engineering team a big hand for how far they got in this competition, how far they went in their first run yesterday, and for spending literally all day today working on their robot in their pit, and then giving it the old college try, quote unquote, on a second run. So that is going to be the last team that we're going to run today. So tomorrow our plan is to start again with our live stream at 8 a.m., just like we did today. Then we will run 6 teams tomorrow. All 6 of these teams are running their second run tomorrow. It's going to be the University of Utah, Colorado School of Mines, Purdue, University of Illinois Chicago, University of Akron, and College of DuPage. In that order, that's what's happening tomorrow. Those are the final 6 teams that have an opportunity to perform their second run. And after those 6 teams perform their second run, it should be about 4 o'clock in the afternoon. We'll need about an hour break, and we will start our award presentation, our award ceremony, around 5 o'clock. Let's just say an hour after the robots are finished with their second run. We intend to start our award ceremony. We're going to be giving out construction award for just the construction event that you've been watching. We're going to give an autonomy award that focuses on the autonomy. The team that performed the most autonomy got the most autonomy points. We're going to give the Artemis Award, which is the overall award for the entire competition that takes into account more than just the excavation and construction. And we'll be giving away the Survey Award. So that is our plan for tomorrow. Thank you for the several thousand people that have been watching this stream today. We really appreciate all the students who have shared our live stream link with all their families and friends and classmates. We appreciate any of you general public that have happened upon this stream and have enjoyed what you've been seeing and have also shared the live stream. Folks that were not able to watch this live can come back anytime and watch the recording of the live stream indefinitely. And so you can still feel free to share links to these live streams if you want to show people certain things, certain particular schools' runs, or certain award ceremonies or something like that. Because YouTube, you can link directly to a specific point in that stream. So we are going to close out today's live stream, And again, we'll come back tomorrow morning, bright and early, 8 a.m. Eastern time. So that is our plan. We really appreciate everybody watching. We appreciate all the teams, all 10 of these teams that have come here. In addition, the other teams, the other 25 teams that didn't make the final 10, they're still around. They're probably experiencing the Kennedy Space Center and Visitor Complex today. We'll probably see some of those teams tomorrow, especially at the award presentation. And with that, we will sign off. Have a good evening, and we will see you all in the morning. Good night.